recordings.
There you go.
Okay, now it is being recorded. Okay.
I started it. I don't know where the recording is going to go then.
Okay. I think Jonathan said it was going to the cloud, so
We go to the
hopefully.
cloud. We got it. Thanks.
Okay, good. Okay, so the first part of the webinar, sorry, of the workshop is going to be introduction and demo, and then the second part of the webinar, which is the second 2 hours, we're going to address user questions directly. See, we already had quite a few users submit questions, so we'll go through these questions one by one and try to answer them as best as we can. But of course, if you come up with any additional questions, feel free to ask, and we'll try to address these as well. Okay, so with that said, let's get started. Okay, so FEBio is a finite element solver that we designed specifically for solving problems in the biomechanics and biophysics research areas. And what that means specifically, I'll come back to this in a minute. So FEBio is a collaborative effort between the University of Utah, where it is led by Dr. Weiss, and with Columbia University, where it is led by Dr. Ateshian. So the development of FEBio started around 2005. So at that time, we and many other researchers in the field were using either commercial packages for doing FE, which has its limitation when you're doing research, or we're developing our own finite element code that we just kept in-house to do research. And so we were kind of in the same boat at that time. We were using another finite element code, but we really wanted to have our own code that we could really explore some new ideas with. But we didn't just want to make a new in-house finite element code. We kind of wanted to take FEBio to the next level and kind of use it to fill this gap that we felt existed at that time. And so with FEBio, what we tried to do is we tried to, on the one hand, offer a ready-to-use finite element software packages that was rich in features that are relevant to the computational biomechanics community. But on the other hand, since we realized that this is still a rapidly evolving field, we wanted to make it relatively easy for users to use FEBio kind of as a jumping board to implement novel algorithms. And so we did that by making FEBio open source, but also by providing a plugin framework. We tried to do our best to keep our documentation clear and up to date. And we tried to provide good support to kind of shorten the learning curve that is needed to learn a finite element application. So when we started, we focused mostly on mechanics, quasi-static mechanical analysis, but over the years, we've added a lot of features to FEBio, more than we can probably cover in this workshop or in this presentation. And so it's just to give you kind of an idea of the key features of FEBio. So you can use FEBio to model a range of physical scales going from the cells and subcellular structures to tissues, organs, and whole body mechanics. FEBio is a true multi-physics code, so we can not only do mechanics, but we can also do various other kinds of physics and combine these physics together in one simulation. We have a huge library of constitutive models, and this is one of the areas that I think FEBio sets itself apart from other finite element codes, and is one of those areas in which that we really cater to the biomechanics community, because we have many constitutive models that allow you to model the complexity of biological tissues, including anisotropy, viscoelasticity, multiphasic materials. We have in our fluid solver many kinds of fluid constitutive models. You can also use FEBio to model material evolution, such as damage, growth. You can include residual strain, active contraction, and so forth. So with FEBio, you can do both quasi-static and dynamic analysis. We also have many kinds of boundary conditions, including contact interfaces, including ones that allow you to simulate transport across the contact interface of either solvent or solutes and various other transport phenomena. So, of course, this is all great, but how do we know that FEBio is actually being used by the community? So over the years, we try to track some statistics that could answer that question. So right now, we have about 12,000 registered users on the FEBio website. The software, which is just the FEBio solver itself, has been downloaded over 60,000 times. We can count on over 500 publications, including journal articles, book chapters, and dissertations. And we are aware of several instructors across the world that use FEBio in undergraduate and graduate courses. So FEBio is used in many different research fields, including soft tissue mechanics, tissue engineering, damage modeling, joint and muscle mechanics, cardiovascular mechanics, angiogenesis, multi-scale modeling, vision, hearing, and much more. So we also are aware of other software tools targeted to the biomechanics community that use FEBio in some capacity. So there is, for example, the Gibbon MATLAB toolbox that does visualization and mesh generation using MATLAB, but also can do finite element simulations where they use FEBio to solve the finite element problems. There is also the surrogate contact modeling toolbox, which is available through SimTK, which also uses FEBio to generate and model surrogate contact models. And then there's also the Open Knee project, which makes available complex finite element models of the knee joint, and they use the FEBio formats to distribute their models. So I hope that convinces you that FEBio is being used out there by the community and has been embraced as a very useful tool for doing finite element simulations within the field. So of course we use FEBio ourselves, and so just to give you an idea what we are using FEBio for currently. So as I mentioned, it's a collaboration between the University of Utah and Columbia University. On our end, we're using FEBio to do various types of joint mechanics. Our current focus is mostly on the hip joint, and then specifically on the mechanics of cartilage, both in healthy and pathological conditions. We also use FEBio as part of a angiogenesis simulation framework, which aims at simulating the growth of new blood vessels. So the FEBio part basically tries to simulate the mechanical effects of angiogenesis. And then we also use FEBio to characterize and visualize complex fiber distributions. On the Columbia side, Dr. Teshian is also doing a lot of work in cartilage mechanics and uses FEBio to simulate various conditions. But he has been doing over the years a lot of fundamental theoretical work, most of it based on mixtured formulations, and all of his mixtured formulations have been implemented in FEBio, including some extensions of these mixtured formulations that allows us now to do fluid mechanics as well as FSI. Okay, so one important thing to keep in mind is that FEBio itself is a command line solver. So basically that means it's a tool that you run from your command line. It takes an input file, it solves the problem, and then it spits out another file. So in order to make FEBio easier to use, you'll need to be able to generate these input files as well as look at the results file. And so in order to facilitate that, we implemented some additional tools that can help you with that. So we used to have separate tools for that, but now we have integrated all these separate tools into a single environment, which we call FEBio Studio. So with FEBio Studio, you can build, you can run, and you can visualize and analyze your FE models with FEBio. So that's what we're going to be using today. We're going to be using FEBio Studio and show you basically the basic pipeline or workflow of using FEBio. So to kind of sketch an overview of what that workflow looks like, so usually users come in with some representation of the structures they are interested in. For example, this can be segmented image data, so they'll have a surface or a volumetric mesh that they can bring into FEBio Studio. Within FEBio Studio, you can make some changes to the mesh, or if you bring in a surface, you can create a volumetric mesh within FEBio Studio. You can also look at various mesh quality measures, as well as make some repairs, some common problems that you might run into. So once you have your mesh set up, it's time to define the physics of the problem, including defining materials, boundary conditions, contact, and so forth. Then you would solve this in FEBio. So as I mentioned, FEBio is an external package, but you can run it from within FEBio Studio. So you don't have to leave FEBio Studio in order to run FEBio, although you can, and I will talk about that later, how you could do that, run FEBio from the command line, that is. But once everything is done, you can bring it back into, you can bring the results back into FEBio Studio, where you can do visualization, animation, analysis, and data extraction. So what we're basically going to do is we're going through this workflow in this order. So we're going to define some geometry, add some physics, solve an FEBio, and then look at the results. I just wanted to make a quick note on the different file formats that we'll be using. So there's 4 file formats that we'll be using, and so I want to give you kind of an initial overview of these files. We'll come back to these specifically, but just so you already have an idea. So there's the FEBio Studio project file, which is not a required file, but it's often handy to keep all the models and metadata kind of together in a single file. So that's what the FEBio Studio project file will do for you. Then there is the FEBio Studio model file. It usually has the FSM extension, which contains the actual model definition. So from this file, FEBio Studio will generate an FEBio input file, which is just an XML-based text file. So you could manually go into that file and make changes with a text editor if you need to. So this file then goes into FEBio. FEBio will solve the problem, and then we'll spit out the results file, which usually has the extension XBLT. So we refer to this file, as the plot file. So the plot file will contain all the results of the analysis. Okay, so that brings us to the demo part. I don't know, can I see the Q&A window in case there are any questions at this point?
Steve, we don't get a Q&A window when we're doing a Zoom meeting, only the webinar. So,
Okay.
people can use chat if they have questions above and beyond what they've submitted prior to the meeting.
Okay, I found the chat window. Okay, so I guess we'll use that for any questions. Okay, so let's switch gears here. So if you want to follow along, then go ahead and open FEBio Studio. So I'm using the latest version of FEBio Studio, which is 1.5. I think if you have an earlier version, you should be able to follow along for most of the part, I think. So if you're not familiar with FEBio Studio, when you open, you probably will see the welcome screen, which kind of gives you an overview of some recent files that you worked on, as well as some recent projects. There's also links to online resources, including the FEBio website, the knowledge space, which is where you can find user manuals, tutorials, and so forth. And there's also links to our forum, where you can ask questions to the community as well as to the developers, because we monitor these forums as well and try to answer any questions you may have on that forum. So on the left side here, we have the repository panel, and this is where we'll start today. So if you click on Connect, then you should be able to see this. So this is an online repository of models that we manage and maintain. So you can find there, for example, models that were uploaded by users, and many of these models were used in publications. And if that is the case, you can usually find information on these publications on the info panel here, including a link that will take you directly to the publication. The repository also contains our test suite, which is a suite of over 300 problems that we run nightly to make sure FEBio continues producing the same answer as it did the day before. So if you're interested in these test suite problems, you can take a look here. They can be a good starting point if you're interested in saying, okay, how do I need to model damage? So you can download some of these problems and see how you need to set it up. There's also tutorials. So these relate to the tutorials you'll find on the knowledge base. And then we recently started giving some webinars that I know some of you have attended already, where we talk about FEBio and FEBio Studio in a bit more detail. And so what we're going to do is we're going to start with the same model that we used in the Intro to FEBio Studio webinar. In fact, most of this demo will follow this presentation quite closely, and the main reason for that is that it actually covers quite a few different features in FEBio Studio that is not too advanced to start with. So if you haven't already, so go ahead and download this project, and the way to do that is to just right click on the project name and click download. Okay, so once it downloaded for you, you should see two models. There is a blank model that we'll start with, and then there's a completed model for when we run into problems. There's some additional resources that we will be using throughout this demo, including a femur model and some additional text files. So that we'll need later in the demo. Okay, so I'm actually going to start here from my special model here. Okay, so once you've opened that blank model, you should see something like this. So what we're basically going to do is we're going to simulate a very simple gait analysis of a hip joint. So this kind of represents a simplified model of a hip joint, and it's actually a simplification of one of the more advanced user projects that you will find here. So it's the hip chondrolabral mechanics project, which was used as a part of one of Jeff's students or former students, PhD students. And so if you're interested in the more detailed model, which includes biphasic analysis, you can take a look at these models. But in this case, we'll keep it simple. So we're just going to start with a simplified model of the cartilage layers and the labrum. So the first part here is represents the cartilage layer on the femur, and then this part, the top part, represents the cartilage layer on the acetabulum, so on the pelvis size, and it also includes the labrum around that cartilage layer. Okay, so the goal here is to set up a simple gait analysis. Okay, so if we now go to our model panel here, we see an overview of everything that is in our model. So currently there's nothing in there except these two pieces of geometry. One is the F cart, which is the femoral cartilage, and then the other is the pelvis cartilage and the labrum. So the first thing we're going to do is we're going to assign some material to these two different parts. Okay, so first we'll work on the femoral cartilage. So if you click on the pelvic cartilage and then click on the H button, it will hide that part. which gives us a clear view on the femoral cartilage. Okay, so let's add a material. There's a couple different ways we can do this. So we can either go to the materials item here, we can right click and say add material, or we can go to physics, add material. So there's a few different categories that you can choose the materials from. They are related to the different kinds of physics that you might be interested in simulating. For the mechanics case, we're only interested in either elastic and uncoupled elastic. And I know there's already been a question regarding that, so we'll make sure to address that later in the webinar. But to keep things simple, we're going to start with an elastic material, and we're just going to pick a neo-Hookean. There we go. So we click OK to add that material to our model tree. So what I would like to do is I would like to create a heterogeneous map that represents the Young's modulus. Right, so quite often we have questions on how can you do that in FEBio and FEBio Studio. How can you create materials that depend on the position? And there's a couple different ways you can do that. So the first way is you can use mathematical expressions. So if you click on this little drop-down box next to the Young's modulus, you'll see that you can either assign a constant value, you can use a mathematical expression. So if I select that, I can type a function of the reference coordinates, and it's important to keep in mind that these are the reference coordinates. These are not the deformed coordinates, because that would add additional complications, but you can use the uppercase letters X, Y, and Z to refer to the position in the reference coordinates. However, what we're going to do here is we're going to assign a map, and the first thing we have to do is create that map. So I'm going to create a map where I'm going to assign a higher value of the Young's modulus on the inside of the model and a lower value on the outside. So in order to do that, we're going to the Build panel, to the Tools tab, and then we click on the Scalar Field button. So the Scalar Field tool allows you to generate scalar fields using kind of like a separate finite element heat transfer problem or Laplace problem. So basically, you're going to assign to certain parts of this mesh a value, and then once you click the Create button here, it's going to solve a finite element problem that solves the scalar problem on the entire mesh, and it's going to give us a scalar field. So in order to create the map that we want to do, we're going to start by selecting the inside surface here. And if you look up here, there's a few selection options here that allow you to select different parts of the mesh. So in this case, we're just going to select the surfaces, click on the inside of the mesh, and then over here, I'm going to set this value to 1 and then click Add. Okay, so this is kind of like defining a boundary condition where all the nodes on the surface will be assigned a value of 1. Next, we'll do the same on the other surface. So we'll click that surface. We're going to set a value of 0 and click Add. Okay, so that defines the boundary conditions for our problem. So also let's give that a map. We're going to name this F cart E. Then on the bottom, make sure this says element data. We're assigning this to material 1, which I forgot to actually assign to this model. So we have to take one step back here. We need to assign this material first. Okay, so to assign the material, what I just did is I clicked on this material. Then with the object selected, click on the plus sign here, and that will assign that material to that object. Okay, so now let's go back. I'm going to have to redo this quickly. So we have a 1 on the inside, 0 on the outsides. We'll call this fcart E. And then click create. Okay, so the data field was added successfully. How do we know what it actually looks like? So we can open our mesh inspector here. So this little icon with the guy with the magnifying glass opens up the mesh inspector. And the mesh inspector is it's a useful tool because it actually shows a few different things. It shows us mesh information. So we have about 8,600 nodes, faces, and about 7,200 elements. It shows you a breakdown of the elements. So in this case, we only have 8 noded hexahedral elements in this model, but if we have different element types, you would see a list of that here. We can look at various metrics over this mesh. So we can look at element volume. We can look at Jacobian. So that might be often useful to spot any initially inverted elements that you might have. There are some shell-related metrics you can look at, such as shell thickness, shell area. There's some tetrahedral related areas or metrics you can look at, so it's quality, various quality metrics. But if you scroll down to the bottom, you see our fcart E, and that's the one we are interested in right now. So if you look, we indeed have a distribution that we plan. So we have a value of 1 on the inside here, and then a value of 0 on the outside there. Okay, so now that we have the map created, we can go back to our model panel and actually assign this map to our Young's modulus. One other thing I wanted to do before we get too far is I want to start using units. So if FEBio Studio, by default here, there are no units displayed on any of these parameters. But if you want to add units, you can add that if you go to the Tools options, and then in the dialog box that appeared, select Units, and then you can set the unit system for either current models, any new models, or all open models. So in this case, we'll just choose the current model, and the unit system we're going to use is millimeter Newton second. So once we select that, we see the units that will be used in this model. So we see a list of the base units here. The length will be in millimeters, the time will be in seconds. And if we look at the derived units, the force will be in newtons. Now, I do want to emphasize, I'm not going for physical realism here. I will not guarantee that this is actual representative of cartilage. So these are just a demonstration of features. But I do want to show that if you are using with a specific unit system, then you can show all the units on your model. Okay, so we have this mesh data created here. So fcart E, copy that name. And then if I go here to the Young's modulus, I can choose maths and then enter this variable here. Now, this would create a Young's modulus that goes from 0 to 1, which is not what I want to do. I want to have a Young's modulus that goes from, for instance, from 10 to 20, from outside to inside. Well, I can actually use these maps also in mathematical expressions. So I can do something like this. Okay, so fcart E goes from 0 to 1. So now my Young's modulus will go from 10 to 20. It will go from 10 to 20, if my math is right. Okay, so you can combine maps within mathematical expressions, which can be very helpful at times. So for the Poisson's ratio, we'll just stick to a constant value. Okay, so that's the material for the femoral cartilage. So now let's do something similar for the other parts. If you right-click on the geometry item here, you can show all the objects. So now what we'll do is we'll hide the femoral part so we have a clear view of the pelvic part. Now the pelvic part here consists of two parts. If we go to geometry here, you'll see it has two parts, and let's just rename these parts. So the first part is the labrum here, and then the second part. And by the way, if you click on a part here and click on this button, it will highlight what part you have selected in the graphics view. So that will be the P cart. Okay, so what we're going to do is we're going to do something similar now for the pelvis cartilage. So if you now click on the blue button here, which allows you to select parts, you can click on the labrum, and we'll hide that for now so that we have a clear view of the pelvis cartilage layer. All right, so let's create a material. So we can go back into add material, or we can just right click on this and select copy, which will copy the material. It does not copy the selection, so we'll have to do that ourselves, but all the material parameters are copied. Now, of course, this F-cart E is not defined on the pelvis cartilage, so we'll just, for now, we'll just set that to a constant value. So let's go ahead and assign that material to the P-cart part. Okay, so we see this is given a color now. The color is corresponds to the material. If you like, you can change these colors. If you click on this yellow box here, you can select a different color. All right, so now we're going back to the build panel.
You assigned
Yes.
it the value of 0 megapascal. You may want to check that before you run the analysis.
Yeah, so we're actually going to do something similar here. So we're going to create a map and then assign that to the Young's modulus as well. So yeah, we'll definitely not leave it at 0. So now, so I'm back on the build panel, tools tab, click on scalar field. So we're going to do something similar, but this time we'll call it P-cart E. So again, the outside will make softer. So we'll make that a 0. And then the inside, make it a 1. I'll rename these materials in a second here, but we need to choose the second material here, and then we will create that, and then hopefully that went correctly. Okay, so the data field was added. So now we go back to our model. There is our P-cart E. So let's rename these materials quickly before we get too confused. So the first one was the femoral cartilage. The second one was the P-cart, and then for the Young's modulus, we'll use the same formula. So we have 10 times P-cart plus 1. I forgot to change this to math. We'll do that first. Okay. All right, so that sets up the material for the pelvic cartilage. So there was one other part, namely the labrum. Let's go ahead and first show everything again. So we can still hide the femoral cartilage, and then we will also hide now the pelvic cartilage, so we have a clear view of the labrum. So for the labrum, we're going to do something a little bit different. So we'll go back to add material. This time, we're going to pick a transversely isotropic material. And the one we'll pick here is the coupled trans-iso-monirivlin. Select OK. Select the labrum here and assign that material to the labrum. Let's go ahead and rename that. So another common problem that users run into is that they want to create some custom fiber organization, right? So this material, so this is a transversely isotropic material, and it defines the fiber property. So there are a couple different ways that you can decide how to generate these fiber distributions within FEBio Studio. So if you look in the model panel here, if you click on this vector option here and select the dropdown, there are a few different options here that you can use to automatically generate the fiber distribution. But if you have a complex geometry, usually that is not going to work very well, and you want to make a fiber distribution that is more, or that follows the shape of your model, for example. And so I want to illustrate a way that you can do that you can create a fiber distribution that follows the shape of the geometry. So in this case, what I would like to do is I would like to create a fiber distribution that kind of follows the circumference of this labrum. All right, so first of all, how do we visualize these fibers? Well, if we right-click on our graphics view here, you'll see there is an option that says toggle fibers, and if you turn that on, and maybe let's go back to one of the other options so we can still see something here. So, so I selected here the vector option, which just assigns this vector to all the fibers in the model. So the vector is just aligned with the x coordinates. So all the vectors are color coded based on an RGB color, right? And so you kind of use this triad in the bottom to help you remember what color corresponds to which direction, right? So a fiber in the x direction, as you can see here, they will all be red. If we turn them in the y direction, they will be green. If we turn them in the blue direction, sorry, in the z direction, they will be blue. If we use some combination, it will also be a combination of these color codes, right? So if we have a vector like that, we have red, green, and blue, all maximized, which will give us a white color. Okay, now we don't want this. We want to create a user-defined map. And the way we do that is we go back to our build panel. We're still on our tools tab here. Click on the fiber generator. So the fiber generator tool works very similarly to the scalar field, except that the output is not going to be a scalar map, but instead it's going to generate a fiber distribution for the material that you have selected here on the bottom. So let me make sure my object is selected here. Okay, and then go back to the fiber generator. So the way this tool works, so it's going to, first of all, it's going to generate a scalar field as it did before, but in order to generate the fibers, it's going to take essentially the gradient of that field and assign that to the fiber property of this material. So how do we do that? Well, the way we're going to do this is we're going to create, as before, some boundary conditions to our Laplace problem. In this case, we're going to select some nodes. So I have here, if you go to the bottom here, so these are all selection tools that allow you to select items on the mesh directly. All right, so the selection tools up here allow you to select the geometrical parts of this mesh, of this object, but the selection tools on the bottom allow you to select items on the mesh itself. So in this case, I want to select some nodes here, and I do that by using Shift and then dragging my mouse. So I want to select one of these lines here. Okay, and with that selected, I set a value of 0 and click Add. Then I go to the other side. Similarly, select some nodes here on the bottom. Assign a value of 1. Click Add. Right, so if we were creating a scalar field, we would be generating a scalar field that is 0 here and then kind of goes to 1 along the circumference. So you can imagine if we take the gradient of that, we will get a fiber that follows along the shape of our object here. Okay, so let's double check. We have here the labrum that we want to select, and I'm going to change this SOR parameter. So actually, you often want to set this to a higher value, like 1.8 or 1.9. to accelerate this algorithm a little bit. And then if you click on apply, you can see it has created our fiber distribution. So remember, the fibers are color coded. So the green ones are pointing in the Y direction and the red ones are pointing in the X direction. Okay, so that is the end of our material parameters with one exception. So let's also fill in these other material parameters for this coupled trans-sizer Mooney-Rivlin. So this is, by the way, so it's a combination of a Mooney-Rivlin matrix and then a fiber contribution. And so the Mooney-Rivlin parameters are the C1 and C2, and we'll just set C1 to 10 and C2 to 0. And then for the fiber components, which are the C3, C4, and C5, we'll just set these to 1. For the bulk modulus, we'll choose 100. And then for the lambda, we'll choose 10. And so this, what this lambda parameter actually represents is the fiber part is represented by an exponential linear stress strain curve. So it's exponential in the first part and then linear in the second part. And this lambda defines the transition point. It is the stretch at which the transition occurs. So if we set this to a large value, we're essentially only using the exponential part of that curve. So that we'll double check here. I think we have finished setting up the material parameters. So let's go ahead and save this first. So if you go to File, Save As, I'm going to put this here. I'll just call this the demo model that we're working on. Go ahead and show everything again and then turn off the toggle fibers. Okay, so next we're ready to set up the boundary conditions and so forth. And what we're going to start first is think about how we're going to represent the gate mechanics. Now, the gate will be driven by applying forces and prescribed rotations to the femur, which is not explicitly represented here. We don't actually need an explicit representation of the femur here because we're going to be using it as a rigid body, but just to illustrate some other capabilities of FEBio Studio, we are going to import an STL mesh and show a few other features related to meshing in FEBio Studio. The first thing we're going to do is we're going to start by creating a new model here. So if you click on the plus button here or go to File, New Model, we can create a new model. And if you create a new model, the first thing you'll see is this dialog box that allows you to select a template for what you're going to be doing, right? And what that is actually used for is, depending on which template you pick, the UI and the menu options are going to change a little bit. It's only going to show you the options that are relevant for that particular type of analysis. Now, we're only going to use this model for the purpose of showing some mesh generation, so we're not really going to do anything with it, but we'll just stick to the structural mechanics option and click OK. Okay, so now that we have an empty model here, if you go back to your repository panel, so you downloaded, if you're following along, you downloaded this, this webinar, and there is a femur.stl that is a model from the SimTK Grand Challenge data, and we can import this into FEBio Studio. There's a couple ways we can import this. So if you go to File, Import Geometry, then you can see here all the different formats that we support in FEBio Studio. So there's obviously FEBio, but also Abacus, ANSYS, LS-DYNA, a bunch of, CAT files as well. There's STL, there's VTK. So you can, we support a variety of different formats that you can use to import geometry into your model. Now, the easiest way of actually importing geometry is just grabbing the file and dropping it on the graphics view. and that will show us the model as well. Okay, so I push the M key here to toggle on the mesh, and this is actually a fairly good mesh for that. You could mesh this and get started with this. Now, just to show you a few different features, what you can do here. If we go to the build panel and then to the edit tab here, you'll see that this came in as an editable surface. An editable surface means that this is a surface mesh, so it does not have any volume elements yet. It's just a surface representation, and it is editable. You can editable. You can, which means you can select things. You can make some changes like decimation, refinement. If there's any problems like holes, you can apply a hole filling algorithm. You can move duplicate faces or non-manifold faces. So there's a few different things you can do to repair meshes or to remesh this part. And I'll show one tool in detail here. So this is a new feature. This is MMG Remesh. It kind of replaces the Decimate tool. So the Decimate tool previously was the standard tool for remeshing a surface mesh, but the MMG-based remeshing tool actually does a much better job in certain ways. First of all, it works with open meshes, whereas the Decimate tool only works with closed meshes. Now, in this case, the mesh is closed, so you could use either one, but let me demonstrate the MMG remesh here. So it has a few parameters. First, the target element size, so we'll set that to 50. If you'd like to have a minimum element size, you can set that as well. We're not going to use that here. There's this global Hausdorff value, which essentially means it kind of says how far you want the discretized mesh to be from the idealized surface representation. So the way MMG works, it actually locally fits a quadratic surface to this mesh, and the Hausdorff measure kind of tells you how far you want that mesh, the discretized mesh, to be from this idealized mesh. So smaller values is going to create very fine tessellation in curved areas. So in this case, we'll set that to 1. The gradation parameter basically says how quickly you want to go from a fine to a coarse area, and usually 1.3 is a good value. So with these values, let's apply that, and as you can see, it created a coarser and more uniform mesh. Now, this is still a surface mesh, so how do we generate a volumetric mesh from that? Well, we go to the mesh panel, and so the mesh panel usually has all the parameters that you can set for creating an actual volumetric mesh. So the meshing method here for triangular surfaces by default will be Techen. In this case, we'll just leave everything as the default value and click apply. So the mesh is generated, but how do you know? Because visually we can only see the surface, so visually nothing has changed. But if we go back to our mesh inspector, it confirms that we now have a 4-noded tetrahedral mesh. We can also look at the quality measures, for instance. So if we go to tet quality, it shows the tetrahedral quality of this mesh. So we have here a minimum value of 0.65, which is good because the theoretical minimum is 0.62, so pretty close. The highest value is 2.7, which is a very reasonable value. So I'd say this is a fairly good mesh. Okay, so now we've created this mesh of the femur. We want to bring it into our demo model here. Now, there's a couple different ways you can do that. You can first export the mesh. So you can go to export geometry, and then you can save it as any of these file formats, including LS-DYNA, Abacus, SDL. Well, not SDL, because that's only going to export the surface. But VTK will also export the volume mesh, for example. But again, there's a shortcut for this, and the easiest way is just go to Edit, Copy Object, Then we go back to our demo model, and then we select Edit Paste Object. And there it is. It is now part of this demo model. Now these two objects, so the cartilage layers and this femur, were created in different coordinate systems, so that's why they do not align. So the next job is to actually align these meshes. And that's basically going to mean, well, we have to transform this femur somehow. Well, we can use the transform tools here. So there's a few icons that you can click. If you click on this one, for example, you get the translate icon, which allows you to translate this femur. You can go to the rotate tool, which you can use to rotate it, or you can go to the scale tool, allows you to scale. If I can grab it, the scale of the femur. So now usually you want to be more precise in setting the transformation, and so you can also set the transform directly. If you go to the edit transform option, you can enter the values here directly, and that's what we'll do, but I'll need my cheat sheet here. So let me just copy these values quickly. And I'll leave this up for a minute for those who are following along. And the scale is the same everywhere. Okay, so let me leave this up here for a minute. If you're following along. Okay, so this sets the translation, the rotation, and the scale of our object. And just to elaborate on this a little bit, so the left column is the absolute values, and then the relative values. If you want to do, for example, just the translation with respect to the current position, you can use the relative options, and you have those for both relative translation, rotation, and scale. So I hope that was enough time for people to copy these values. And if you now click OK, it positions the femur where we want it. Okay, so now that we have a geometry for this mesh, we can assign a material, and the material that we're going to assign is a rigid body. So to make a rigid body, we right-click here on the materials item again, select add material. In our category, we now select the other category and then select rigid body. Okay, so we've added our material. Now we assign it to the femur. So we click on the plus sign to assign that. So the size of this femur is a little big. It kind of dominates our model here. So what I want to do is I want to cut off a part of this femur here so that we can not be too distracted by the size of this femur. So let's do that first. So we go back to our build panel, and notice that although we got our object, we actually didn't get the mesh here. If we hover over this icon, it should tell us what's going on. And it says the object is not meshed. So because we imported this as an editable surface, it didn't copy the finite element mesh. So we have to rebuild that quickly. Okay, so we regenerated our mesh. So now what we'll do is we'll convert this to an editable mesh. And just like with the editable surface, if we convert this to an editable mesh, we can directly manipulate the finite element mesh. So there's quite a few different tools that you can do with it. You can do some partitioning of the mesh. You can repair certain problems of the mesh. You can invert elements. We also have an MMG-based remeshing tool that remeshes the volumetric mesh. There's also a simple mesh refinement tool, and there's a few other tools that you can use to directly manipulate the mesh. Now, in our case, we just want to delete a part of the mesh. So to do that, we click here on the element selection tool, then using Shift and dragging the mouse, we can select some elements. If you only select the surface layer of elements, then you may have to check this box here. And then you can click on delete, and that deletes that part of the mesh. Okay, let's go ahead and save this just to be sure. All right, so if we go back now to our rigid body material, there's a couple parameters that you can set here. Now, none of these are going to be relevant except for the center of mass, because we're going to be prescribing a rotation of this femur. So we need to know where this femur is going to rotate around. And what we want to do actually is we want to rotate it around the center of this sphere defined by our femoral cartilage. So, well, that means we need to know where that center is. Fortunately, there is a tool that will tell us that directly. If you go here to the main toolbar and click on the measure tool, you get a dialog box that allows you to measure various kinds of metrics. So you can measure distances, angles, area, volumes, and so forth. But in this case, we want to fit a sphere to a selection. Now to make the selection, it will be easier if we hide the femur. So if you click on the femur, click H, then you've hidden it. So now I can select the femur. If you click on the F shortcut key, it will focus on your selection, which allows you to see the femur, the femoral cartilage a little bit better. All right, so first we're going to select the inside of the mesh here, and we're going to select the actual facets on the finite element mesh. So if I select this option here, select connected, if I click on that here, it's going to select all the facets that are within this angle criteria. Right now, if we want to select the entire inside, we can just increase that angle, click select, and it has selected all the facets on the inside of this mesh. Okay, so with that selection active, so we go to the sphere fit tool here, make sure this selection only is checked, and then click fit. And as you can see, it fit a sphere to that selection. And now we can just copy the X, Y, and Z coordinates of the center of the sphere into our rigid body's center of mass. Okay. And just a reminder, if you have any questions, feel free to ask them in the chat window. So Dr. Weiss and Dr. Eteshian are ready to answer your questions. And if it's anything related to the presentation, of course, I'm happy to answer any questions as well. Okay, so let's just rename this quickly. We'll call this femur. All right, so we've set up all the materials. It's time to set up our boundary conditions. Now, before we do that, we're going to think about the actual analysis steps that we're going to be performing. So we're going to apply two steps. We're going to have a loading step where we're going to apply a force to the femur to kind of have it settle in place. And then in the second step, we're actually going to prescribe some rotational kinematics. So the first thing to do is go to steps, add analysis steps. We're going to pick a structural mechanics, and the first step we'll call loading. And then we'll go ahead and add the second step, and we'll call that, let's call that gate. So there's a question here regarding the remesh. Is it possible to constrain the remesh to preserve sharp edges? The answer is yes. So the MMG tool, which is a third-party tool that we're now using in FEBio, does a really good job in preserving sharp edges. So it kind of has its own algorithm that it uses to detect sharp edges in the model, and you have some parameters to control that, but it will preserve any sharp edges that it encounters. Okay, so let's take a quick look at some of the settings here in our analysis steps. So first of all, we're going to be doing static analysis, but we also have the option to do dynamic analysis if we wanted to. And the other thing I want to draw your attention to are the time settings. So there are 10 steps, excuse me, and each step is 0.1. So this is in seconds. It doesn't show the unit here, which is something we'll have to add. But this step size is in the units that you have selected, which in our case would be seconds. So we have 10 times 0.1 seconds, which means that the first step will go from time 0 to time 1. The next step, the gate step, has the same time stepping, so it'll essentially goes from time 1 to time 2. Okay, so that's important to keep in mind. All right, with the steps added, let's start adding our boundary conditions. So let's first set up our gate kinematics. This means we have to apply a force, first of all, to our rigid femur. So we're going to add a rigid constraint. Make sure this step says initial rigid material is femur, and then we'll select prescribed rigid force. So for the rigid material, yep, we have femur, then the force is going to be in the Z direction. And for the value, we're just going to set that to 100. Now, what does that actually set up? So we're applying a force of 100 newtons in this case. And again, the units are not displayed here, but this is in units of Newton. So, but in addition to adding this force, behind the scene, FEBio Studio has also added what we call a load curve to this boundary condition. And so what the load curve is going to do, it's actually going to ramp up the value from 0 to 100 over the time steps that we have set in the analysis step. So how can we actually see that load curve? Well, if you go to the curve editor here, so the curve editor is where you would be editing all these different load curves that you would have in your model. And if you now look under the rigid constraints, not sure why this shows up 3 times, but there's let's do that. Okay, so I just selected the filter load curves here, and then it showed the rigid constraint here. And as you can see, it's just a default ramp, which will ramp up the value from 0 to 1. So this curve gets multiplied by the value you have set in your force property here, right? So essentially, the force will ramp from 0 to 100. Now we'll come back to this when we talk about the prescribed kinematics. So I'll show you a few more things on the curve editor. So first of all, let's change this. We'll call this Z-force. Now the Z-force applied in the initial step, and the initial step is a little bit of a special step because basically any boundary conditions or loads or whatever that you apply to the initial step will basically persist throughout the entire simulation. So it will remain active during both the loading and the gate step. Now the rigid kinematics, so the prescribed rotation, which we'll add now, we're only going to apply that to the gate step. So first let's add them. So in this case, we go to fixed rigid displacement, rotation. So we'll select the femur and we'll select X rotation. And then we'll copy this. So this will be the Y rotation. And then we'll copy this again, and this will be Z rotation. Okay, and then let's double check everything. So the step will select gate. It's only going to be active during the gate step. Same thing for the Y rotation. And then the same thing for the Z rotation. Okay, double check quickly. Okay, looks good. So similarly to the force, FEBio Studio also applied load curves to these prescribed rigid rotations. So let's go back to our curve editor. And now, looks like it didn't update this. Oh, I applied a fixed. My apologies. That's not the right one. I chose the wrong boundary condition here. So we have to go back and select prescribe rigid displacement rotation. Okay, so let's redo that quickly. So we have X rotation. We'll set a value of 1 for now. Call that Y rotation. Call that Z rotation. Okay, so again, only in the gate step. Y rotation, okay. Oh, gate. All right, let's double check quickly. So we have X, Y, and Z. Okay, so now if we go back to the curve editor, there we have our load curves. All right, so let's talk a little bit about how we can edit these curves. So first of all, we can add new points by just shift click on the graph itself. We can select these points and move them around. We can change the interpolation time type of the curve. So we can interpolate using linear functions, using step functions, and then various smooth representations. Another thing we can do is we can enter mathematical expressions. So we can say sine of pi times t, like that. So we can change also the extent type, which basically defines what the curve is going to look like outside of the range that is defined by the points. So this is useful, for instance, for making cyclic curves. So that's another way. Let's just go back and leave this at constant. Another thing you can do is you can digitize an image to create a curve. Like you can set a background image here. Either you select it from a file or in the newest version, and you might not be able to do this yet, but you can just drop a figure on that and it'll set it as the background image. And so now you can go ahead and digitize this curve. Now, before you can digitize it, you have to align the coordinate systems, which you can do with this button, and it's going to be hard to see on this white background, so you'll just have to trust me that there is a rectangle being drawn that you can now define the range of. So the range goes from 1 to 2.2 on the x-axis, and on the y-axis it goes from 0 to 0.6. Okay, so that has aligned our coordinate systems. And I just realized this curve is defined over time 0 to 1. So what we're going to do is we're going to, first of all, to make it a little bit easier to work with, define these initial points over the range 1 to 2. So now let's realign the grids. Okay, so now we can start digitizing these curves. So first we'll align the range, and then we can start adding points. Like that. Okay. So that's another way you can define a curve. So you can clear that background image, then you'll just have the curve left. And then the final method, and that's actually the method that we'll use, you can just import it from a file. So again, if you go to that repository panel, there's some additional files here that define the kinematics of the rotation. And so we'll just go ahead and import these files. So we have the x-axis, y-axis, or y-angle and z-angle. Okay, so that defines the kinematics of our problem. When does the first part end? Is it 9:30 Mountain Time?
And
Yes.
technically in about 10 minutes.
Okay, so we're almost there with setting up the problem. So let's go through the rest a little bit more quickly. You know, we can come back to some of these issues if you have any questions in the second part of this model, but I do want to get to the point where I can at least run the model.
Steve,
So
don't forget to create the interface between the rigid bone and the cartilage.
yes, so there's a few more things we have to do here. We have to set up some boundary conditions. So first of all, let me show everything. So on the femur, on the pelvis side here, so we can imagine that there is a pelvis on this side here, which is going to be fixed. So we're just going to add a fixed boundary condition on this side, and we'll also we'll add that surface as well. So that's the back side of the labrum. Now we also want to tie the femoral cartilage to the actual femur, and we do that through a rigid interface. So if we select, it's kind of difficult to see here, but I clicked here on the inner surface of the femoral cartilage to select that surface. Then we go to contact, we select rigid, click on OK. We assign this to the femur, and our surface selection is already done. So that ties that mesh to the femur, and then the only thing that is left to do is define the contact interface between the two parts here. And we do that by adding a sliding elastic. Where is it? There it is, sliding elastic. So we'll need two surfaces here. We'll pick the outer surface of the femoral cartilage and assign that to the primary surface. And then I'll go ahead and hide a few things here so I can see the inside again. So for the inside, which is going to be the secondary surface, we are going to select the inside of the P card, and we're also going to select the inside here of the labrum. All right, so I'm just shift clicking around this perimeter to get everything selected, and then we can assign that to the secondary part here. Then for the contact parameters, there's a few changes I want to make here. So first of all, I want to turn on the auto penalty so that we get a penalty factor that is based on mesh elements and local stiffness. And then I think the penalty is 0.1. And then the search radius, which kind of tells us how far out we want the contact algorithm to try to detect the contact. And I believe that is it. So I think that is now everything, and we are ready to run this model. So to run this model in FEBio, we just click on the run button here. So there are a few different options. We can we can talk about that maybe in the second part a little bit more detail if there's any questions about this. But basically, the default configuration will just run this on your local computer. But I do want to point out that you can set up remote configurations, which allows you to run this model on a server. So FEBio Studio will send the model to the server. We'll start FEBio on your server. Of course, you'll have, assuming that you have FEBio installed on the server, and then we'll pull the results back in at the end. So, and then, so once we're ready, you just click run. Now, in the interest of time, I'm just going to pull up my finished model here, just in case we run into any problems. So this, it doesn't run that long, but I just don't want to risk into running into any issues with this model. So I'll just load the final result here. So this shows now the post-processing side of FEBio Studio. So the interface has changed a little bit. So on the left side, you'll now see the post panel, which has kind of like a model tree of the model, but it only shows like things that are related to post-processing. So there's a displacement map, which will show the deformation on the model. There is a color map that you can use to show various metrics. And so in fact, there's some shortcuts up here. If you just click on this drop-down button and then select, for instance, the effective stress, we can take a look at the stress distribution. Sorry, my Zoom windows are in the way here. So you can see the animation here. So I can drag on the different points on the timeline. I can also just run the animation automatically like that. So you see there's two steps. The first step is kind of hard to see, but I can limit. So if I limit the time range between 0 and 1, we can kind of focus on that first step, and you see that we have a load being applied that kind of pushes the femur into the socket. So we also have a material tab, which allows us to hide certain parts. So if we want to look, for instance, at the insides of the pelvis cartilage, we can hide everything else and see what's going on the inside of the pelvic cartilage. Now, since we used contacts, we probably want to check to see how well that contact is enforced. And there's a couple of different ways, we can do that. But the easiest way is just by adding a plane cut, which just shows a cut of the model. Let me turn off the actual plane itself, and then we can look at how far the two objects are penetrating. So it's pretty good, but we are getting a little bit of penetration. So probably could have done a little better job on the contact. So some other things we can do is look at the values of specific elements and nodes. So if we click on an element, for instance, here, we can go to the post panel where you see a lot of different features you can do. So you can add various kinds of plots like vector plots, tensor plots. You can do isosurface maps and slice maps. For visualization of fluid flows, you can have streamlines, particle flows, and volumetric flow visualizations. So we can actually import 3D image data as well and allow you to kind of volumetric rendering or image slices, things like that. So, but in this case, we just select new graph because we want to look at the value of the stress here at this element. And so the way to do that is select the metric that you want to look at. So let's look at effective stress, for example, of this element. We can add more than one element, so we can look at several different values at the same time. There's also some tools on this panel that might be useful. And then I'll end after this. So some of the tools, you can set some options for the graph. itself for the data, so you can set things like the marker types and the length, and so most of the visualization tools that you would expect for visualizing graphs. There's also some curve fitting tools that might be helpful. For instance, if you want to get the slope of this first part here, you would select the source. So in this case, it would be let's see here. Let's do the green curve. So we'll do this one. Now that fits a curve to the entire domain, which is maybe not what we really want. So let's just select a few points here and then set selection. And now we can fit a slope to just the initial part to kind of get an estimate of the slope of the initial part of the curve. Okay, so there's a lot of other features we can do here. And again, depending on how much time we have left in the second part, I can show some additional demonstrations. So for instance, you can also create recordings. So you can do video capturing directly from within FEBio Studio. There are integration tools that allow us to integrate over volumes or over surfaces, and a few other things that might be useful. But I think it's time to take a little break, so we'll stop here. And then in the second part, we'll switch gears and we'll start by answering some of the user questions that were submitted.
So we currently have planned a half-hour break. If there are any specific questions that are related to the demo, though, we could take those now, in like for 5 minutes out of that half-hour break, and then just come back to the same meeting, and we'll start up at 10. So maybe we'll pause here to see if anyone has any questions.
Okay.
And you can enter your questions in the chat window.
Would they be able to just say the question themselves?
I'm not sure if they can unmute themselves or not. I think we might be able to allow that. Let's see.
So regarding that last question, where
Yes, they can unmute themselves, I think.
Okay, let me add one thing to the last question that I just noticed here. If we can see the stress in each constituent of a solid mixture. So that's actually something I recently added. So there is a way to do that right now in FEBio Studio. It basically requires entering a custom parameter field. I forgot the exact syntax, so I'm hesitant to demonstrate it right now, but there is a way you can actually look at the stress of the individual components of a solid mixture.
Okay.
Let's just run a quick test. I see, for example, Julian Ray. Julian, can you unmute yourself so we make sure that?
Sure. Can everyone hear me?
Yes.
Yep.
Thank you. Okay. So let's take a half-hour break. Don't leave the meeting. Just mute yourselves and stop your video, and then let's come back in 28 minutes, like at whatever your local time is, and then we'll reconvene. At that point, if you don't have immediate questions, we're going to go through the list of questions that you sent to Jeff in the order maybe in which they were received. I don't know. What do you think, Jeff? Or do we do the breakout sessions?
I think we probably can hop around a little bit, as some of them,
quick.
as we discussed, might be better dealt with offline, in a different kind of approach. But we can take a look and see what makes most sense to address in the time that we kind of have left, and the other ones we can work with individual users, after the workshop if necessary.
Very good. Okay, see you in 27 minutes now. Steve, one of the questions that was posted was whether you can enter material properties based on imaging data. And Jeff said you can use the mesh data capability. So maybe at some point, if there's a quick way to demonstrate that, that would be nice.
Yes, that would be very helpful. Thanks.
Steve, you're muted.
Okay, so I don't think I can demonstrate that because this is actually something we're still working on. So we're working on being able to import image data in FEBio Studio, and that's getting to a point where we might start releasing part of this capability. But the next phase would be to use that image data to actually assign it to various mesh properties, but that has not been implemented yet. So I know people have gotten around that by writing their own scripts that kind of map image data to their mesh once they have the FEBio input file. And then once you have the input file, you can bring it in FEBio Studio and the mesh data will be preserved. But we don't have a method yet directly in FEBio Studio that allows you to map from image data onto mesh data.
Is there a way to import nodal or element-based values from, say, a text file and assign them to elements?
The only way we can do that right now is through the FEBio format. So if you create an FEBio file that has the mesh data sections, then you can import it into FEBio. But that's another thing we haven't added yet. So that's something else we can look into. I think that you can actually store data in like a VTK file or something. I think that file allows you to store both the mesh and the data of that mesh. That might be probably the easiest way of supporting this kind of capability.
So I have done that in a project where, let's see, I'm going to try to find it. I have too many things open on my desk, sorry, but I'm going to try to open a file that was shared with me by a user who happens to be a student at Columbia, and I collaborate with his advisor. So I'm going to try to locate that file and see if I can show you something about it. But yes, it requires writing scripts and things like that.
Are you essentially making a custom mesh data section where you associate each element with the property?
Correct.
Okay.
So
Yeah, maybe it will be helpful if I show you the output that FEBio Studio created for this model, because it will have a mesh data section in there. Yeah, so shell thickness is currently also written to the mesh data section, but so this is the fiber data that is assigned to this material, and then let's see, where's the actual? Oh, these are the material axis, and then here are the maps. So in this model, I'd call them emap1 and emap2. So it just goes in the file as scalar data that assigns a value to each node of that element, right? So there's 8 node hex, so each node has 8, or sorry, each element has 8 values associated with each of the nodes. Now there's actually a few different formats. There's some additional attributes you can specify here, so that you can specify like one element per, one value per element is another option. And I think we have this documented in the user manual, but I'll have to double check. But this is something, in theory, you should be able to import this back into FEBio Studio, and the element data will show up there as well.
So one
So
of the aims of our, oh, go ahead, Jordan.
yeah, let me share my screen quickly.
Do I have to stop share?
No, it's okay. I can just overwrite.
Ah,
I'm
okay.
gonna, sorry. So here's a brain model. So this is just the outer skull, but basically this particular, skull, let me hide the, well, I'm not gonna hide anything. Let me just take a section through it. So what you're seeing here is the inside of the brain, okay? And in this particular case, we're looking at brain swelling on the assumption that when cells die, the inside, the negative fixed charges of the intracellular content becomes exposed to the brain tissue. So the fixed charge density is based on how much damage this brain was subjected to during some kind of traumatic, brain injury. So there's a separate analysis that was done with data from the company that we were working with they did the analysis of the traumatic brain injury. Then we converted their kinematic data to FEBio, and we ran it through our damage model. And our damage model extracted the damage variable between 0 and 1. And we said, if it's 1, that means 100% of the cells in that volume were damaged. And if it's 0, we said 0%. Then we associated the fixed charge density when all the cells are damaged. So now we wanted to do a multiphasic swelling analysis. So if you run this, solution over time, you can see the brain swelling. It's going to swell more where the fixed charge density is high. So you can see that I'm actually plotting the referential fixed charge density here. And so, the bluer it is, the more damage, the more negative it is. So actually these regions, this is a very, a fatal injury. You can see pedestrian fatal injury. So there's a lot of damage everywhere, but the fixed charge density, the referential fixed charge density was entered in, manually. We wrote a script that would output this file format. You can see here we're mapping, the fixed charge density to this particular finite element set. And this is the amount of damage, if you want, that's associated. This would be 84% damage, 86% damage, but each element has a different value. So, and then we multiply that by the fixed charge density associated with this particular material. So if I go back to this element set, and if I look for it, I find that it's associated with this particular material, which is multiphasic. And I've got this map, which is a number from 0 to 1 multiplied by -60, which is the fixed charge density when you have a maximum amount, all the cells have died. So this is an example where the script that you have to write is how to output these numbers into a format like this. That's it, element per element. So you need to know which element, has how much of that property that you want to associate with. Does that address?
Yeah, it doesn't seem too bad.
Okay. Very. Okay, Jeff, I hand it over to you in the order in which you want to take care of questions.
Oh yeah, as related to what we were just discussing, I was going to say that enabling the use of image data to define various input parameters for FEBio is one of the aims of our current grant proposal, as Steve mentioned. So I think it's safe to say within the next 12 months, we should have some initial capability for doing that. And that should help people who actually have things like, CT data or other types of image data, and they want to extract, for instance, various material properties or physical properties from that data and use it in the analysis. In terms of the questions that were sent to us ahead of time, we kind of assembled those in a Word document. Let me see if I can find that. Okay. Let me share my screen. Let's see Okay, so Gerard and Steve, what are your feelings? Do you want to hop around to this document, or just go from top to bottom? It's basically ordered by participant's last name.
I don't have a preference.
So the first question is from Shami Moore, and I have prepared the model that I can run, but it will take 10-15 minutes to demonstrate this one. So maybe first we answer the quick questions.
Sure, I think that's fine. So we can start with these questions from Jason Cox. So hopefully this first question, Jason, is kind of apparent to you as Steve's just shown you. You know, the XML formatted input file that's what FEBio takes as input. And so this is very analogous to the INP file that Abacus uses. And in terms of the file format for that, you know, all of the details of the format of the FEBio input file are described in the various chapters in the user's manual. So let me see if I can just show you what I mean by that. So if you go to the knowledge base, that's where we keep all of the manuals and other things. Let's see here, manuals, user manual. And so the free format input section essentially goes through and talks about each of the different sections of the user manual. And we give examples of the XML code for each of the parameters in the input file. So like for a sample control section, you can see that you have this, and then a closing label as well. And then for instance, for solver, we have a number of different parameters. And all of these parameters are kind of described in the subsequent chapters. So you can learn about what they do. Now, what you've been watching today is effectively a case where that FEBio input file is generated based on what you do in FEBio Studio. And so you can choose to use FEBio Studio, which we certainly hope you will be able to do to make your models or to assist in making your models, or as needed, you can hand edit the .feb file that's generated when you ask to run FEBio in FEBio Studio, or you can ask FEBio Studio to write the model file at some point while you're creating it. And so that would take care of these first two questions here. Okay, so this right here, I think this is actually probably a question for Gerard, because it refers to plasticity materials in FEBio. And if I remember correctly, I believe the manuscript for the reactive plasticity capability materials in FEBio are still under review. Is that correct, Gerard?
Yes, it's been an endless review. It's been a tough review. However, the quick answer is we have the von Mises yield criterion, we have the Drucker criterion. We don't have Drucker-Prager, but those are easy to add, you know, criteria. So we haven't documented the plasticity feature yet, but if you're like eager to use it, a couple of users have reached out to us and we've shared a copy of the manuscript with, you know, with them. So if you want, just email me and I will send you more information.
Okay, great. And I can address this parallel computing question. And so FEBio is parallelized using OpenMP, which is a parallelization model for shared memory computers. And so a shared memory computer is a computer that has multiple cores or processors, but they all share the same memory pool. And so this is in contrast to a distributed memory parallelization model where you have multiple individual computers and each computer has its own memory bank. And so the parallel computing capabilities for FEBio work best and on these shared memory computers. And so in terms of parallelization, a very large portion of the code in the FEBio solver that is compute intensive has been parallelized using OpenMP. And so it's really just a matter of finding a computer that supports parallel computing, in other words, has more than one core, which is pretty much any computer these days, and setting the environment variable that tells FEBio how many cores to use. And there's a variable that's described in the manual. Let's see if I can find that section real quick. I think it's towards the beginning. Using multiple processors. And so you can see here that there's a variable that you set in your environment depending on which compute environment you're in that determines how many cores or threads or processors that FEBio will use. And so the limitation to parallel computing with FEBio is that our default linear equation solver, which is quite robust, is a direct linear equation solver. And so direct solvers only scale to kind of a finite number of processors. And usually with FEBio, we find that number, even for the largest problems, to kind of max out around 12, maybe 16 cores. And so for using the direct linear solvers, that's really, you don't need to set this value any bigger than that. In fact, if your problem is small, you might not even need to set this value to anything. But when you start to get into problems that have over 100,000 degrees of freedom, it certainly makes sense to enable parallel computing and set this variable to a reasonable value. And in terms of optimizing the value, the easiest way the way that we normally do that for ourselves is we run the model with a few different values, and determine for that model the optimal number of cores or threads to use. And the other part of the compute intensive aspects of FEBio are memory usage. And so it's important to remember that the memory required to solve the linear equation system that's repeatedly analyzed in FEBio each time step scales quadratically with the number of degrees of freedom. And so the memory requirements go up very quickly as you start to get into large numbers of nodes and thus large numbers of degrees of freedom. And that's simply a characteristic of using assembling the stiffness matrix and how many degrees of freedom are in the stiffness matrix, how much memory it takes to store the stiffness matrix. The other aspects of that stiffness matrix storage are whether the problem results in a symmetric matrix or a non-symmetric matrix. So for instance, most elasticity problems that don't involve contact result in a symmetric matrix. If you add contact into the model, it depends on which contract algorithm you're using, whether you'll have a symmetric or non-symmetric matrix. And then once you get into the mixture materials in FEBio, you're automatically going to have a non-symmetric matrix. You can choose to symmetrize it, but generally speaking, you want to store the matrix in a non-symmetric format. And so that kind of affects the size of the memory. So the best kinds of parallel computers for working with FEBio are those that will allow you for any given job to select up to 16 cores and as much memory as you can afford, right? So on personal computers, it's pretty standard these days to be able to fill them up with 64 gigabytes of memory. And for most models up to 500,000 degrees of freedom, that's going to be perfectly fine. If you're talking about, kind of supercomputer type systems, it's really common to have terabytes of memory available on those systems. And that's to accommodate multiple users. I think some of the people who run larger models with FEBio using the direct solver, as I say, might be up to 1 to 2 million degrees of freedom. Now, at this point, it's probably worth just discussing briefly the difference between a direct and an iterative linear solver. So there are a couple of major differences. One, first, the direct solver is going to be the most accurate, and it's always going to be the more robust. And in fact, it's safe to say that in terms of iterative linear solvers, less than 5 or 10% of the types of problems people run with FEBio can be effectively solved with an iterative solver. There are a few classes of problems that seem to be really amenable to this. The types of things we encounter in biomechanics that work well with iterative linear solvers are things like maybe you want to model the explicit structure of a chunk of cancellous bone, and you've got micro CT image data, and you want to convert that micro CT image data into both geometry and maybe map the Hounsfield number onto the model, so you have a position dependent modulus. And you want to compress this piece of bone, simulate compressing it to figure out effective properties. So in this case, you have no contact. You have a single material type that just has various material values for, say, modulus. And so that results in a stiffness matrix that's very well conditioned, but quite large usually, because those problems commonly have millions of elements. And so that's the type of thing that works really well with iterative solvers. And so the iterative solvers can be an option for certain classes of problems that will allow you to expand the size of models that you can effectively solve with FEBio into the millions of nodes and elements. But the drawback is that, generally speaking, they work very poorly with problems that involve contact. or any sort of situation that produces the traditionally relatively stiff or poorly conditioned stiffness matrices that are kind of characteristic of solid structural mechanics. I'll stop there. Let's go back to the questions. Okay. All right. So this is one. So Gerard, you said that Adam's question, you needed a bit more time to talk to him about this. Is that right?
Well, I can I can actually respond the first part. I mean, I cannot help him with this specific plugin, now without learning more about it, but I can give some general information. So the question here is whether, there's mesh locking that occurs when you use shell elements with an uncoupled formulation. So, so mesh locking can occur for two reasons. One, when you use an uncoupled formulation, whether it's a shell element or not, it may lock. And two, because it may not be able to conserve the volume as much as you want. There may not be enough degrees of freedom in your element to do that. And two, shell elements can lock for reasons that have nothing to do with the uncoupled formulation. Shell elements can lock if the shell element is very thin compared to the span of your geometry. So the specific question, where is Adam? Oh, you're here, Adam. Right. Okay. I can see. So if I'm not answering your question, stop me, if I'm like going off on a tangent. But let me share my screen and just show you. So you were asking about modeling an aneurysm, right? So I don't have the geometry of an aneurysm. I just created this hemispherical shell. This particular one is uses 4-node quadrilateral elements. This one here uses 8-node quadrilateral elements. I have a couple more that I can open with 3-node elements like this one, and I ran them all. I just wanted to kind of highlight what we have. And this one here, which is going to be a 6-node triangular element. Am I going to, are my instructions going faster than what you see on the screen, or are you able to see more or less at the same time? More or less at the same time. Okay. So basically, I ran this model, all of them, and I'm going to show you, the results quickly. So what I have here is this inflation, right? I didn't overinflate. I did a little bit of inflation. Then I took one of these nodes, the one at the center. So I'm going to do an orthographic projection and look at the front. So no, look at the top. Then it'll be easier for me to pick the middle node. And then I looked at the displacement as a function of the pressure or as a function of time in the y direction. So I'm going to show you this curve, how much deformation. So it's the same amount of pressure applied to all the models. The models that deform less are going to be the ones that we suspect are locking, okay? I also want to say the following. All of these materials, all of these shells use a Mooney-Rivlin material with a shear modulus of 0.4 megapascal. So C1 is half of the shear modulus. And the bulk modulus is very high, it's 200 megapascal. So if I want to look at how much of the volume has been conserved, I cannot look at the relative volume, I have to look at the shell relative volume. So you have to remember to output the shell relative volume plot variable because it's not there by default. And if I run this analysis, and again, in my case, so you can see that it's pretty much remaining equal to 1, except at the very edge where it's very difficult for it to conserve the volume because I constrained both the outer surface and the inner surface of the shell to be fixed. So on this rim, if you want, you don't see the thickness, but I guess I could actually show you the thickness of the material. I just have to remember where to do this. Shell as hexes, yes, and it should be the top surface. So can you see if I turn off, so suddenly you can see the thickness, right? So there's a front face and a back face to the shell. So you can see the thickness of the shell. So what I did is I fixed this edge, the inner edge and the outer edge are both fixed. And I did this using fixed displacement for the outer rim and the fixed shell displacement, okay? So as a result of fixing this, it's impossible to conserve the volume exactly at the bottom rim. Of course, now it all gets averaged because of the way that I'm displaying, so don't let that confuse you. I have to go back and turn this off and redisplay it. Okay, there we go. Okay, so then, but everywhere else it's being conserved. So I am satisfying the isochloric deformation that I expect, except at the boundary, which is to be expected. Now let me show you the results for, I don't know if you can see the text, but that's too much. So I have try-3 elements, so try-3 shells, try-6 shells, quad-4, quad-8. And I have this quad-4 EAS, which is more accurate, that avoids the shell locking that I mentioned. And then for the sake of comparison, I did a quad-4, which uses a neo-Hookean, which is compressible, and I set Poisson ratio to 0.499. So when you look at the results, you will see that all of them displace pretty much the same amount, except the green one, which is the neo-Hookean material, which doesn't have the 3-field formulation that avoids locking. So I picked a compressible material and I picked a Poisson ratio close to 0.5. So I'm definitely getting the mesh locking due to the uncoupled formulation. This has nothing to do with the shell formulation. And then the try-3. The try-3 shell simply doesn't have enough degrees of freedom, even with the 3-field formulation. So it uses the 3-field formulation because the try-3 shell in effect is actually a prism element, right? You have the front face is a triangle, the back face is a triangle. So really it's a prism. And for prism elements, FEBio does enforce the 3-field formulation for prisms that have 6 nodes. So nevertheless, the try-3 element, the shell element, locks, right? And so that tells you that you should never use try-3, but the good news is you can always convert your try-3 mesh to a try-6 mesh. So you can, you see the try-6 is actually invisible below these 3 lines. It doesn't lock. So the try-6 doesn't lock. And then is there mesh locking? Are we getting the case where because the element is so thin compared to the surface area? It turns out that for the model that I picked, for the thickness that I picked, that ratio is about 100 to 1, 1 to 100. The thickness compared to the diameter of this circle is about 1 to 100. The mesh locking would occur, the shell locking would occur at 1 to 1,000 or more. So as a result, the the Q4 EAS is not showing much better results than the others, which is great news as long as you don't have shells which are exceptionally thin. Okay, so that's the answer. Don't use try-3 if you're using an uncoupled formulation. Always use try-6 if you have no choice but to use triangular elements.
And then do I need to explicitly set the 3-field formulation, or will that automatically set with an uncoupled material?
By default, when you use an uncoupled material, the 3-field formulation will kick in for quadratic elements. The 3-field formulation is not used for all quadratic elements, whether shell or solid, because it's not necessary. And the results that I showed you prove that. Why? Because there are enough degrees of freedom to enforce conservation of volume in a 6-node triangle or in a 15-node pentahedron or in a wedge. Okay, so it's that the question was asked on the forum: could I use the 3-field formulation for a hex 20 element or for penta 15? You can change the code, and in fact, in one of the forum responses, I even pointed out where you can change the code. But the reason why I know the answer is I changed the code myself to check it out, and it actually makes the results a little bit worse. So you don't want to use the 3-field formulation except for linear elements. Now, if Jeff or Steve have something to add to this, please do so.
I've never tried the 3-field elements with higher order elements. The main element that we implemented it for initially is the 8-node hex. So for that element, you have a trilinear interpolation of the displacement and a piecewise constant interpolation of the pressure and the Jacobian of the element. And that's specifically to avoid locking with that 8-node element. My understanding is for higher order elements that you can achieve the same thing with the same approach, but then you would use, for instance, for a quadratic element, you would interpolate the pressure and the Jacobian linearly over those fields. But I don't believe so. Gerard, you're saying you've tried to create those elements and didn't?
No, so I just used the default 3-field formulation. So for hex 20 elements, it would only have one J value. It wouldn't be like a linear interpolation of the determinant of the deformation.
Yeah, so in summary, we have this 3-field formulation only, I believe, implemented for the hex 8 elements. Steve, can you comment whether there are any degenerated
and the penta 6?
The pents as well?
Penta 6, yeah.
Okay. Yeah, so those are the only 2 element types that use the 3-field formulation. I think I sent an email response to this question as well. So I just want to mention that, and Gerard will, I think, back me up on this, that unless you're really very important to you to approximate near incompressibility, in other words, your ratio of your bulk modulus to your shear modulus is like 1,000 to 1 or greater, there's really no need to use the 3-field elements, and then there's definitely no need to use the uncoupled materials either. So those uncoupled materials are designed to work with the 3-field elements, and so if you have a situation, say where your bulk to shear ratio is 10 to 1 or even 100 to 1, you can use the coupled materials and they'll automatically use the standard displacement-based elements for structural mechanics. And our experience is that they work quite well. There's also issues with using uncoupled materials for materials that are relatively compressible. They oftentimes result in some non-physical behavior. Without going into the details, I would just say that if you have like a bulk to shear ratio of 1, definitely don't use the uncoupled materials for that type of situation. You use the coupled counterparts, which are available in FEBio. All right, let's see what we have here.
Thank you.
Yeah, no problem.
The only thing I want to add to that is that there is an option in FEBio to choose whether or not you actually want to use the 3-field formulation, even if you choose 8-noded hex elements and uncoupled materials. So you can actually force FEBio to use a standard displacement formulation as well.
And what would the, maybe you don't know off the top of your head, but what would the like input for that be, and where would I put that in the file?
Yeah. You might pushing me on my knowledge of the top structure of the input file, but there is a mesh domain, and so there's the mesh domain section, and then the solid domain, and I think actually it's an attribute, something like this, you would specify in the input file. I'll have to double check the exact syntax, but it's something like that. So maybe if you want to know, shoot me an email after the workshop, and I'll double check the syntax and maybe send you an example file. And I realized I wasn't sharing my screen, so you probably didn't see anything that I was just doing. So yeah, so shoot me an email, and I'll send you an example file.
Okay, thank you.
Okay. It's just a command that says use _3_field_hex, and then you make that equal to 1.
Or a parameter of the mesh domain.
Control section.
Oh no, that's the old format. So in the 2.5 format, it was just a flag in the control section. But in the 3.0 format, it's a flag in the mesh domain section. So you can actually turn it on or off for each of the domains that you're using.
So Gerard, I'm not sure if you want to save this for an offline discussion. I'm assuming you looked at this one.
I looked at this one. This will take, I can answer it. Sarah, you're here. So let me give you a quick answer, and then if you want a more detailed answer, you can reach out to me by email. Right, my email is ateshin@columbia.edu, so you can always email me. But let me say the following: what you have is you shared with us this very nice diagram, and Jeff, keep it on there. Actually, why don't you share you are sharing your screen, sorry. So I actually was able to create a model for you. I'm going to quit and restart. And so I want to say this. FSI is not suitable for having a solid material floating through a fluid. So the kind of formulation that we use in R in FEBio does not allow us to do this. However, the problem that you have is actually, so this dimension that you have is a millimeter, and this from here to the center is 2 millimeters, but you have a particle that's only 25 micron in radius. So even if you wanted to create a finite element mesh, it would be a very difficult problem to solve because of the disparity in the scales. So this would be more suitably done using what we would call a multi-scale analysis. But the problem is not trivial, and it can be done partly. So you want to follow a particle that enters through your microfluidic channel and then either exits to this side or exits to this side. And you're interested in figuring out the deformation of the particle, correct? You need to correct me if I'm wrong. You need to say something.
That's correct.
Yeah, okay. So basically what I recommend, and I created here a fluid analysis, okay? So first what you would do is you want to model the fluid flow. So this, I don't know how much velocity you wanted, but you had the dimensions. So I put the dimensions and you can see the mesh. I created the mesh by first creating this square and then 4 rectangles, and I then welded them together. And I created biased meshes because we're going to have 0 fluid velocity at the wall due to the no slip condition. And for now, I made the fluid have the viscosity of water, and I applied a tiny pressure. The fluid pressure that I applied is 10 to the negative 6 megapascal, which is 1 Pascal. And then I ran the analysis, which in this particular case ran very fast because it's actually a very simple flow problem. And so if you look at the fluid pressure as a function of time, you can see that the fluid pressure rises and then eventually reaches steady state. So I'm going to turn off the mesh. This is the fluid pressure. So remember, you're applying fluid pressure from this side and this side. I'm assuming the fluid is entering from both sides and it's exiting from here and here. So you can actually visualize the fluid velocity, and you can see it enters here and it exits here and here, right? So what we've done is the fluid analysis. What I suggest that you need to do next is to do a fluid solute analysis, meaning add a solute whose diffusivity is calculated to represent a particle that's about 50 micron in diameter, 25 micron in radius. To do this, you need to use the Stokes-Einstein relation, which you can look up, for example, in Wikipedia. So I'll type Stokes-Einstein equation, and we're probably going to get a hit on Wikipedia. So here on Wikipedia, Stokes-Einstein equation says that if you have a spherical particle of radius r, in your case, r is 25 microns, you use the Boltzmann constant, the temperature, whatever you want it to be, 6 pi, and eta is the viscosity of your fluid. You can extract what is essentially the diffusivity of your particle. Then you run a fluid solute analysis, which currently is not yet available in FEBio. This is the missing part. Okay, it's not currently available using a viscous fluid. You can do it using a multiphasic material, but then it'll be a different behavior. So as a result, you would need to wait until we release the fluid solutes module, and I'm giving a presentation at the conference tomorrow on that module. Anyway, then you would be able to track the particle as it flows through. But then what you want is to figure out the relative velocity between the particle and the solvent. So the relative velocity, because the particle, the sphere, is not necessarily moving at the speed of the solvent. It may or may not. It depends on the problem. If there is a relative velocity, then you use the FSI module in FEBio, where you put a sphere that's deformable in a fluid that's flowing with the relative velocity that you calculated from your solute transport analysis. So you put that velocity differential between the solute and the fluid. And now, of course, you can create a domain which is not 1 millimeter channel, but you can create a domain that's maybe 2 or 3 diameters of your sphere. And you can even make it a 3-dimensional domain, because that's what it is. You have a sphere. Then you have to apply boundary conditions that prevent rigid body motions of the sphere. So you would have to constrain a few nodes judiciously. Again, we can discuss those in details, but then you can watch how the fluid flow would deform the particle. Okay, so that's that. But let me say this. For a problem like the one that I analyzed here, the diffusivity of a sphere, I actually did the calculation myself for the diffusivity of a sphere of radius 25 micron. The diffusivity is on the order of 10 to the negative 9 micron squared per millimeter squared per second. That's an extremely low diffusivity, which means that the Peclet number is very high, which means that the particle is actually moving at the velocity of the fluid. So you actually don't need to do the solute transport analysis, because your particle is actually going to. So if I wanted to, so this is a fluid mechanics demonstration. Let's use this vector field to track how a fluid particle would move. And in reality, if a fluid particle moves at a velocity of the fluid, your sphere is going to move exactly the same way. So I'm going to use the particle flow tool. I'm going to select the nodal fluid velocity, and I'm going to show the path lines. And what I'm going to do is I'm going to temporarily hide the vector. Now, the path lines are going to be drawn inside of your material. So you got to make the domain transparent. So you would have to make the domain transparent. And then what's going to happen is we're going to run the analysis, and you can see that actually, I'm going to come back here, but I should probably pick a step size, which is much smaller, because everything is moving so fast. Let's see. You see? So again, if I actually, because of the pressure that I applied only 1 Pascal, but 1 Pascal was actually enough to cause the velocity to be on the order of, right here, we're at 10 millimeters per second. So the velocity is probably way too fast for your microfluidic channel. And Steve, why am I not able to get smooth lines here? For the particle flow, I thought I had, are
they just moving too far between time steps, or?
They're moving too far between time steps. That's correct. I should probably have solved this problem with many more time steps. Okay, anyway, the point is you can follow the particle. So as a result, the diffusion analysis is not necessary, Sarah. So what you want to do is you essentially, if the particle is moving with the fluid, then that means that there's no relative motion. All you need to know is what's the pressure in the fluid surrounding a sphere. And that pressure is the pressure gradient that you see here, the fluid pressure. You see, that's the pressure field. So now all you have to do is figure out how to apply a pressure field around the spherical gel and figure out how it deforms. And since the pressure gradient varies from location to location, depending where your particle starts and where it goes through, the pressure gradient will change. And so you can figure out how much the particle is going to deform based on the pressure gradient. You don't need to do a solutes analysis. Okay, so that's my answer. Does that seem sufficiently clear?
Yeah, thank you. So you're saying for my particle to not define the geometry, just see the pressure of the nodes, right?
So if ultimately what you're interested in is the particle deformation, but you want a particle that's subjected to this flow, what I'm saying is a dimensional analysis, which is kind of what I gave you, explains that you don't actually need to explicitly solve for the motion of an actual sphere through the fluid, which is good because FEBio is not able to do that. So what you need to do is you need to solve that problem that I solved for you, but for whatever pressure you're going to apply. I can share that model with you, just email me. Then what you need, you get the pressure from this and you apply that pressure field on a particle that's just an elastic analysis, your particle, and you subject it to a pressure that's non-uniform around it, and you figure out how much it deforms. That's it.
Yeah,
So
thank you.
it's-
That makes sense.
Yeah, it's not so hard. You don't actually, this
Yeah.
is how engineers solve problems in practice. You don't have to necessarily solve the real world problem because of all these scale disparities.
Thank you very much.
Well, Jeff, you're muted.
Thank you. Let's go back to the question and answer file. Let's see here. Okay. Jingji had a question about shear thinning. It sounds like you've already spoken with him in the past, Gerard.
On the forum, I think. Was it on the forum? No, because he had sent the questions to you and I had responded by email. Are you
Okay.
here, Jingji? His camera?
Hi, yes, I'm here.
Okay. So,
So this has been answered already.
well, you said you had more questions. I want to know, what are you trying to model? Are you trying to model a fluid or a shear thinning fluid or a shear thinning solid? Are you trying to model toothpaste or are you trying to model saliva?
It's more like a toothpaste. Yeah.
Okay.
So it's rather a shear thinning solid, and which we have done some rheology on it, and we can model it with a power law modeling. So I'm trying to understand if there's a way we could translate what we observe from experimental settings into a simulation, because we want to mimic it in different applications. So that's what I was trying to understand.
So if it behaves more like a solid, then really it should be modeled using the plasticity module rather than a non-Newtonian fluid. Then in the plasticity module, the question becomes, how does one take a shear thinning rheological model, that we know? So I would say it's a fairly advanced topic. I don't have a simple answer, but I do think that FEBio can solve the problem. We may have to write extra code for it, but if you want, then again, I invite you to reach out to me by email with a little bit more details. And this applies to anyone who's asking a question, that I can answer. I'm happy to set up one-on-one Zoom meetings. I don't know when. You just reach out to me and we'll pick a mutually convenient time, so that we can discuss in more detail what can be done. So why don't you do that, Jingji, right?
Yeah, sounds good. Thank you.
Okay.
Will do.
Okay, so next is Hirit, who works with Jonathan Van de Geest at University of Pittsburgh. And we've actually already corresponded about some of these questions, specifically the first question. We talked about various ways to reduce the size of the .feb text file by writing, for instance, fixed boundary conditions all together on a single line rather than line by line. There were other questions about indexing into elements. So I put Steve's name down here for that. So Steve, I wasn't sure if it's, so normally we use like node sets and element sets to, define boundary conditions. And I was curious whether or not we can define those based on a continuous range of numbering or whether they have to be explicitly listed.
Yeah, so right now they have to be explicitly listed. And what FEBio Studio actually does, and this is more an issue with FEBio Studio than with FEBio, is that, for instance, if you have prescribed displacements on the same surface, you would specify a different boundary condition for X, Y, and Z. And so what FEBio Studio actually does, it will recreate the same node set in the FEBio file repeatedly. So that's kind of a limitation on FEBio Studio's side, because on the FEBio side, that limitation does not exist. Like you can reuse you can reuse the same node set for different boundary conditions. So so that's something we'll have to address on the FEBio Studio side. Now, the other thing that we cannot do currently is we don't have any kind of shorthand notation like they have in Abacus, for instance, where you can just define an element range to define an element set. But that's something we can easily add, and I'm happy to look into that.
That's
So I
what
think,
I passed along to them. I told them that would be a pretty easy feature to implement and probably handy for a lot of people. So
yeah, I agree. I think we used to have something similar like that when we specified the node sets or surface sets as part of the boundary condition, but that has been deprecated. And so now you kind of specify all the geometry related issues or definition as part of the mesh definition. So you can take that outside of the model file. And that's another thing I want to mention is you can separate your model into different files. So if you have, if you have multiple models that, for instance, all use the same geometry or the same mesh, but that only differ in, material parameters or boundary conditions, then one thing you can do is you can just store that mesh in a separate file, and then only you can only specify the boundary conditions in a separate control file, and that's something you can actually do from within FEBio Studio. So maybe I can just quickly show that if I share my screen. Share screen. Share. So when you export a model from FEBio Studio, so export FE model, let's just, that's fine. We'll just give it that name. So you get this dialog box here that allows you to specify some options for exporting the FEB file. And so if you click on more, you get these additional checkboxes that you can use to export parts of the mesh. So if you only want to export the mesh, you would just select none and then click on geometry. And so now it's only going to store the geometry or the mesh in a file, and then you can come back, you do that again, and this time you export everything except the geometry, and so that will create your control file. Now, currently you do have to make a small edits in that control file to make sure that FEBio can find the geometry file, and so that's something we'll have to add. So right now you have to go back into the control file and tell FEBio where to find the geometry section. So, but that's, that's something helpful or useful that you can do, especially if you have large models and you need to make manual changes to the FEB file. So often these models can grow tens or hundreds of megabytes large. It might be difficult to edit in a text editor, but since the bulk of the part is going to be the mesh, you just export the mesh in a separate file, and then you only have to edit the control file.
Thank you very much. If I wanted to do like script this, will it be using the include command? Just if I want to do this in MATLAB?
Right, yeah. So if you use so there's two commands. There's the include command and there's the import attribute, right? So the include command will include an entire file. But if you only want to import specific sections from another file, you would use the import tag. And I think we have that documented in our usage manual somewhere.
Yes, thank you.
Okay, good.
okay, I'll go back to sharing the screen with it. Let's see here. There it is. Okay, so the next part of Hewitt's question was about errors that she's encountering running on the supercomputers of the Pittsburgh Supercomputing Institute, or Supercomputing Center rather. So sometimes the job stops without any error, and sometimes they were getting a segmentation fault error. So Hewitt provided us with one of the .feb files that she's been running. And the text file itself is about 1 gigabyte, but Steve looked through this file and found that in that particular file there was a formatting error. This formatting error was embedded within many lines in the file, and so we concluded that the file had been generated by a script that Hewitt had written, and so correcting that error. So it turns out that error with old versions of FEBio pre 3.0 were generating a segmentation fault. But with newer versions of FEBio, it was catching the error and exiting gracefully. Neither, of course, was going to run past that input line. And so correcting that error in trying the file with the newer versions of FEBio, it did run correctly, or did at least get past that input stage. And the other question about job stopping without any error, this makes me wonder about the computing resources. Okay, and so when FEBio starts, it goes through an input phase where it reads in all the stuff that's in the input file, and it begins allocating memory, and it has to allocate memory for various data structures, but ultimately the big memory allocation is for the stiffness matrix. And so if you get to that point, and FEBio is trying to allocate memory for the stiffness matrix and runs out on the computer, so the computer just doesn't have enough memory to store the stiffness matrix, then FEBio is going to stop. My only question is how gracefully that will occur, and perhaps Steve could comment on that. Would it give a seg fault, or would it give an error about insufficient memory available, Steve?
I think it depends on, am I muted?
No, you're not.
No, okay. I think it depends on when FEBio runs into trouble. So the most likely place for that is going to be in the memory allocation of the linear solver. And I think that one might be hard to catch. I'm pretty sure it's going to seg fault. So because that happens in a third-party library that didn't provide a mechanism to really gracefully handle that kind of exception. So if you run out of memory during the allocation of the stiffness matrix, or actually during the allocation of the inverse of the stiffness matrix, the factorization, then it's probably going to crash.
So let me just comment about how to kind of track this down. So you need to have some understanding of what physical memory resources are available on the system that you're running on, and so that should be available from the PSC staff. You should be able to say, I'm running on this node with this name, and could you tell me how much physical memory is available? And oh, by the way, can I expect that other jobs will be running on that node as well? Okay, and that should at least give you an idea if you have a chance, of getting all that memory. Now, the more difficult part comes in actually seeing how much memory your code's trying to allocate, and doing that in real time. And so there are some, I believe you're using Slurm for job submission. Is that correct? Okay, so there are some tools available within Slurm that allow you to monitor information about your jobs as they run. And so I would work with the PSC staff to see which tools they have available for you, but I'll just mention a couple that are generally available in Slurm environments. One's called S-Control, and that lists detailed information about a job while it's running. This is useful for troubleshooting. There's also a third-party piece of software that you can get on GitHub that they probably have installed called Slurm Browser. And that gives you information about CPU and memory usage from your running job. So like if you get this thing running and pop it up on your screen before your job is executed, then you can watch the allocation of physical memory by FEBio. And if it seg faults, you'll get a pretty good idea of how much memory it was trying to allocate and whether that amount of memory was more than what's available on the particular hardware that you're using. Okay. So there's no hard limit in FEBio. You can try to allocate as much memory as you want. Whether that's going to work or not is kind of depending on what sort of box you're running on.
Yeah, that makes sense. Yeah, and I rerun the large job. I gave it 15 hours and it ran out before it finished, so I have to give it more time.
Oh, well, at least it got started. Did it take any time steps? Oh, good.
It had about 3 steps. Yeah.
Perfect. All right, so that did solve the problem then. That's great.
Yeah.
Okay.
Thank you very much. I appreciate it.
Yeah, no problem. Okay, anything else here? Or are you good now? Everything good?
Yes, but just to clarify my earlier question about the mesh convergence, I put it in the chat earlier.
Oh, yeah.
I was trying to create a mesh convergence plot while I'm varying the mesh size. And right now, the way I'm doing that is by outputting specific, nodes around a specific XYZ location in space. And I do that in every job. But I feel like the XLPT file is it has more data, and that might be easier. So I was wondering if there is a quicker way to output results in the XPLT file as well. Or I don't know what's the best way.
Okay, I think I understand what you're trying to do. So you have, as you refine your mesh, you have nodes within a certain sphere radius or something like that, or box perhaps, and you can identify those nodes a priori, I assume, if you have the input file.
Yes.
So you know the node numbers that you want to output for.
Yes.
And you're just asking how to get that data out so that it's written at runtime to a text file or something like that.
Yes, I write it to a text file right now, but I was wondering if using the XLPT file, if that one is faster, or I don't know.
Oh,
better
okay.
way.
Well, the XLPT file is designed to be used with the post-processing side of FEBio Studio. It's a binary file. It does have a well-defined format, and you could certainly, write a script or a program that would search through that file to find your data. I'm concerned that your models are probably so large that can you open your models in FEBio Studio or?
No, it crashes when I open it. I just open the input file in a text editor.
Yeah. Well, suffice it to say that the nodal data that you're looking for are probably in the plot file, unless they would need some calculations, for instance, in the post-processing side. But since you say that you can't open the model on the post-processing side, I'm assuming that's not a concern then. So yeah, I mean, you could in theory index into the plot file and find the same data. I'm not sure if it would really be of any advantage though. It seems like you've got a way to do it right now that's working.
Yeah, that's fine. Yes.
Okay.
Yeah,
all right, great.
Thanks. Can I comment though? So you're running fluid FSI models, is that correct?
No, they're solid.
Solid?
Yes.
Is there, okay, so do they have a large number of elements because the meshing was based on some image-based acquisition, or is this the mesh refinement you actually need?
So it comes from multi-photon microscope data, but I was doing the mesh convergence plot. That's why they're larger files. The finer simulations are big.
Okay. I mean, there are ways to, refine the mesh locally where things are happening and keeping it coarse where things are less important. So I strongly recommend spending all that extra time to create a really good mesh. This is like running an experiment. Running a finite model is a very time-consuming effort. To just dump it on the supercomputer and hope that it's going to run, it could take a month of supercomputing time. But if you spend a week creating a beautiful mesh, and you're going to pull your hair out by the end of that week, but then it's going to run in another week, it's much better that way, So I just want to say, philosophically speaking, one shouldn't think that creating the mesh is a trivial, quick step and the time consuming is just the analysis. It's not necessarily the case.
Okay, let's move on to Andre's question. So Andre wants to know how to best model heterogeneous materials like cells and how to optimize the stiffness distribution based on a measurement of strain distribution. Okay, so it's kind of a couple of different questions here. So the first one's about modeling heterogeneities. I assume you want to explicitly. So if is Andre here?
Yeah, I'm here. I think you kind of touched on the way to do this earlier on. So
yeah, I was
going
to say, yeah,
the first part. It's more the optimization, I think.
Great. And so that's where I was going to, pass off to Steve. So basically, I think, so FEBio has built-in capabilities for parameter optimization. So effectively, what it allows you to do is to run FEBio in a loop iteratively to optimize various aspects of your model inputs so that the predictions from FEBio line up with, for instance, experimental measurements like you're talking about. And so Steve can, I think Steve can probably do a better job than I can explaining.
Yeah, first thing, I'm not sure I fully understand the goal here, but I can give you a bit of an overview of what we currently have as far as optimization options, and then you can comment on whether or not these will address your needs. So let me start by pulling up the user's manual here on the topic of optimization. So basically, the section that you'd be interested in looking at here is the objective section, right? So the basic goal that FEBio does.
Sorry, one thing. Are you supposed to be sharing your screen?
Oh gosh, sorry, I keep forgetting that. All right, hold on. Where's the button? Here, share screen. Okay, there we go. Sorry about that. All right, so I'm in the user's manual here, which again you can just find on the knowledge base page on the FEBio websites. And then in chapter 7, we talk about the optimization capabilities. And so this is kind of the general formula that the optimization module solves, right? So it tries to minimize this objection function phi, where A is a set of parameters that you would like to optimize. So for instance, material parameters. And then the xi, yi are data pairs that you provide as part of the problem definition. So this can be, for instance, experimental displacement force or time force data that you acquired. And then the function f is really kind of what defines the optimization problem. And so if you go to the optimization input file and then the section on the objective section, so these are the different models, if you will, or scenarios that we currently support in an optimization module. And so the first one is the data fit. So that's kind of the one that we supported for the most time. And so you come in with some experimental force displacement curve, and then you want to try to find the material parameters that fit that curve, or at least that generates the same displacement force curve in FEBio that then tries to match that experimental data. So the second one, the target one, is where you want to achieve a specific value for an output parameter in FEBio. So for instance, you have a load that you apply on a model and you have a rigid body that you want to figure out, okay, what's the load that I have to apply in order to rotate the rigid body to a certain angle, right? So you would input that desired angle as your targets, and then FEBio will optimize for the force that achieves that specific target value. So the other one is element data, and element and node data are very similar. So basically what you do is you provide a list of element values, for instance, desired stress values, what you want to have in specific elements. And then FEBio will solve the optimization problem. So again, for instance, it will try to optimize material parameters that give you the stress values at these element data. Or in the case of node data, it will give you, for instance, you want to optimize for nodal displacements. So in that case, FEBio will try to find the material parameters that give you the desired nodal displacements. So we have some examples in our test suite, and I kind of pulled them up aside here. I go one up, user questions, optimization. So we have several optimizations in our test suite, and you can find these in the repository under test suites. So I hope they're there. Yeah, optimization. So there are these examples, and so these examples show you some of these different model scenarios. I'll just show you one that might be of interest. I think it's the 5. Sorry, I need the OP file. No, that's a data fit. Was it the 6 one? Here, so this one, the OP06 is an example that uses the node data. All right, so in this example, we have an input model, which is specified in a separate file. And the input model is just a usual FEBio model, so it just defines basically the forward analysis. And then the optimization, which is a separate input file then describes the optimization problem. So in this case, so we're using the node data objective, and we are going to optimize for the material parameters here that achieve a desired y displacement, right? So uy refers to the y displacement. And so this is the data that you would input. So you'd input the nodal displacements that you want to achieve for these specific nodes, and then FEBio will solve this problem, try to optimize. In this case, I think this is probably a Poisson's ratio of the material that is defined in the input problem. Okay, so these are the options we currently have, and so I guess my question now to you is, does any of these sound like they might be helpful to you?
Yeah, no, that's actually perfect.
Okay, good.
No, that should work just fine. I guess so I run them because I was doing this not in FEBio, I was doing this like in Python, just with my own optimization script.
Mhm.
So I was like curious to learn more about if FEBio had anything built in, and it does, so it's great.
Okay.
So when you're running from the terminal, do you have to specify both? Because it sounded like you had two input files, so you specify both of them in order.
Right. So yeah, so let me show you how you would run this on the command line. Although you can run this through FEBio Studio as well. But on the command line, the syntax would be, so I just went into the directory of these files, and then I just type FEBio3-I to specify the input file, and then -S to specify the optimization input file. So I don't know if my font is kind of small. You can see this. So it's -I to specify the input file, and then -S to specify the optimization input file, and then it'll run. And so this was a very small problem, so it ran pretty quickly, but it basically spits out all the attempts it made. So it uses a constraint, a Levenberg-Marquardt method in the background that solves the actual optimization problem. And so this is the output of that optimization. And at the end, you get the optimized value, the final objective value, and then the function values at that optimized parameter. Okay, and so this also goes into a log file, which is here, this OP06 log file.
So Steve, in the interest of encouraging people to use FEBio Studio, would you mind just quickly showing how one can do this optimization in FEBio Studio?
Yes, so let me show, first of all, how to, where is it? OI06, where did it go now? Oh, here. Okay, so you can import this this input file, and I just want to show how you would generate an optimization file for that. Now, it doesn't support all these different objective functions, but at least you can generate kind of a template that you can then customize to your specific needs. So you would go to FEBio generate optimization file. So that kind of takes you through a wizard where you can set the controlled options. So it's, Levenberg-Marquardt or constraint Levenberg-Marquardt. There's also a Powell method in FEBio and a scan method, which is kind of sweeps, does a parameter sweep. But you'll have to edit the file manually for that. So let's just leave that for default. You can then set the parameters that you want to optimize. So in this case, I think it was just a Poisson's ratio, specify initial values and a range. Then you can specify the objective parameter, which in this case was just UI, and then you can generate some points here based on a function, or you can just import them from the clipboard. So you can just copy paste them, for instance, from an Excel spreadsheet. And then you would export that file. Okay, so So let's assume I wrote this file now and I called it OP06, right, which is the actual one that we want to use. So I would then go to run. I'll have to go to the advanced tab here. I'll have to change my working directory. Let's give that a different name so we know it actually worked. And then we also have to overwrite the command. So at the bottom here, you see the command that FEBio Studio will actually execute. And what is missing from this is the optimization file. So you would just add that. And then hopefully that will work. Okay. Well, there's no results to load, so we'll just know, but you see it ran the optimization file in FEBio Studio, and you have the results there as well. So you could do it through the FEBio Studio as well.
Thanks, Steve.
Easy enough. Thank you so much.
You're welcome.
All right, great. So I guess I'll take the screen back, and we can continue on with the questions. I just wanted to mention that the stuff that we're talking about, you can actually find the details in the manual. Any sort of questions about command line options you can find in chapter 2 about running FEBio. And so you can look at the different options in this location. So let me get that Word file back open. Let's see. Okay, looks like the next question is from Julian Ray. It's about plugin development, and I think Julian's looking for an overview of the process.
Yeah.
Is that okay? Great.
That's about right. But before we move on there, I had a quick question about optimization from the last response.
Okay.
I noticed that there was a fit for, it seemed like, Poisson's ratio. Could there be fits for multiple optimizations for multiple parameters at once? Maybe that's possible.
Absolutely, you can add as many parameters as you want. So,
okay.
Want the screen back?
Either manually. Yep.
Sorry about that.
No worries.
It's your turn.
I'll remember by the end of this workshop to start sharing my screen. But yeah, you can add as many as you want. So I won't go through the full syntax here, but
sure.
You can just add, and then you can add a Poisson, a Young's modulus or something like that. Right. So you can add as many as you want, and of course you can edit the input files directly as well. So you can just add here parameters that it will optimize for.
Okay.
I think that Julian was explicitly interested in, for instance, rigid body reaction forces. Is that what you were getting at, Julian? You said
no, actually, that was somebody else actually who asked that in the chat. Okay. No, but yeah, I think they were asking something similar. In this case, my other follow-up question regarding optimization, here the objective parameter is displacement in the y direction. Just from the top of your head, could we potentially have the Jacobian, the determinant of the deformation gradient, as the objective parameter?
I don't think that one is available. So the values that you would specify here are any of the same variables as you would use for the output section to the log file. So that would be, let's see here, output, log file, node data class. So these are the variables that are supported in the node data. And then for the element data, you would have these options. So it looks like, well, it does,
okay.
there it is. So yeah,
there's a J there.
There's a J, yep, and the components of the deformation gradients are there as well. So yeah, so I guess you can do it.
Potentially I could. Okay.
Yep.
Yeah. Okay. So that was my question regarding optimization. But yes, I was interested in perhaps an overview of plugin development for custom material properties. In my case, I'd like to prescribe fluid production, but not using Starling's law, just actually a simpler case where I prescribe volumetric fluid production in a biphasic material. So that's my specific issue. I mean, I think other people might be interested in a broader overview of plugin development for custom material properties.
Yeah, absolutely. So it sounds like you've tried something, but you ran into problems. So maybe after this workshop,
Okay.
feel free to reach out to me. I'm happy to figure out what is going on and see if we can
I
solve
appreciate
it.
that. Yeah.
Yeah, so to give you a bit of a general overview, so in FEBio we support plugins. I'm hearing some echo. I don't know if maybe someone is not muted. Anyways, let's quickly go where to find it. So we'll go to Developer's Manual. And so that's probably the best place to start if you want to get started with FEBio plugins, right? Because it contains a kind of an introduction on plugins, some basics, and some examples, some more detailed examples. And so in your case, you're developing a material property, which is not the same as a material, but you would actually have to do very similar things to developing a material plugin. So the only thing that will be different are the specific functions that you would implement. So for an elastic material, this would be stress and tangent. And in your case, for solvent supply, I think is what you were looking at, and you would have to implement different functions. So, but the basic process for all the plugin development is very simple, or is very similar. So first of all, you kind of identify what features you want to add. So is it a material property, boundary condition, and whatnot. And then you'll have to figure out the base class that you would have to start from if you want to create a new feature. And so for the case of a material, or at least an elastic material, this would be the FE elastic material. So once you've identified your base class, you can start writing your plugin. And that usually means creating your own class, right? So in this case, there's an example here that shows a neo-hooking material. And so this is derived from the base class FE elastic material. The base class will usually have some, let's see what happens if I click on that, some virtual functions that you have to implement. Let's see here. I haven't used this in a while myself, and it looks like there's something missing here. I'll have to take a look at that. So, but in any case, let me go back. I was looking at here. So you have to implement usually some virtual functions, and these are determined by the base class. And so in this case, for an elastic material, you would implement a stress and a tangent. So once you've done that, so that's the hardest part of the plugin. Once you've done that, there's a few other things that you have to do in order to make sure that FEBio can recognize your plugin. And let me go to my example here that I had prepared. So in this case, and this example, by the way, comes right off the website. So there is a special page on the website called plugins, where you can download the plugins that we currently have available in FEBio, at least the ones that we are aware of, that people have shared with us. So if you're developing a plugin, keep in mind that we are very happy to host the plugin on our website, and so that other users can find it. And so the example I'm going to show here is the neo-hooking PI, so the neo-hooking plugin. So it implements the neo-hooking material, which FEBio already has, of course, but it shows it that you can also do it as a plugin. So this file has a bunch of comments in it that hopefully will help you kind of get started with plugin development. And like I said, so the crucial part are the implementation of the required functions, which for an elastic material is a stress and the tangent. So just to show you what that actually looks like. So in FEBio, we have some some classes that can be used to represent tensors. So you can very easily write out tensor expressions like this, which makes it easy to translate your mathematical expressions that you have derived into code. So usually there is a very close correspondence between the actual equations and the implementation in FEBio, which I think is very helpful for developing these plugins. So once you've done your coding of the required function, there are also some additional functions here that you have to implement. Let me go back to the manual here. So it talks about that in the plugin basics. So the required functions. So you have to basically communicate with FEBio and inform FEBio on which new functionalities that you are adding into this plugin. So once you've done that, you can build the plugin. And so in this case, I've built this plugin. This is built as a DLL on Windows or a shared library on Mac or Linux. And then if you want to use that plugin, there's a couple ways you can do this. But the easiest way is just have the plugin in the same file as your model files, and then you can just run the model. So in this case, the input file is that, and then you just tell FEBio of this plugin by just adding the -import command line, and then you can add the plugin directly on the input file, and then you'll run it. Or FEBio will load that input file or load the plugin file. And let me show that actually quickly. So if I don't specify the input file, so FEBio will just load the plugin, and don't worry about these failed plugins. These are other plugins, but you can see on the bottom here, success loading plugin neohooking pi.dll. So you'll know that FEBio was able to load the plugin, and then you can run the model directly from within FEBio using that plugin. Okay, so that was a very short overview of plugins. I think we're going to be making a webinar on plugins in the near future. So if you are interested in learning more about plugins, so keep tuned for that webinar. I don't know when that will be. We haven't put it on the schedule yet, but I expect that will be one of our next webinars that we will present. So does that kind of help? I know this is
So
kind of
it
a
seems like,
whirlwind.
yeah, the essential files are the header file, the .cpp source file, and the .dll file.
Yeah, there's one file I forgot to copy. Let me see if I can find it quickly here, which implements these required functions that I mentioned. So again, you can find the source code of this example online. So there's this dll.cpp that implements. Where is my here? Let's do that. So this is the additional file that you would implement. So there's a bunch of required function. So the get SDK version basically ensures that your plugin will work with FEBio, or the FEBio version that you have installed. And then this is the plugin initialize function is basically the one that communicates with FEBio and informs them of any new functionality that you are adding.
Okay. All right. I'll give it another shot and then follow up with you if I run into more problems.
Okay, sounds good.
Okay. Professor Ateshian pointed out that we had skipped a question at the beginning. So I wanted to go back and grab that. Let's see here. Share screen quickly. Okay, Shami Moore had a question. It would be helpful for me if it's possible to demonstrate a sliding phenomenon of biphasic tissue against a rigid body, and if possible, fluid recovery by unloading during a creep test. Gerard, I want to turn it over to you.
Right. So Shamgar, originally I figured, oh, I can just do a demonstration in a breakout room with the two of us, but we decided for now we're not going to do the breakout room. So I'm just going to share with you the model that I created and just explain to you the basics. So you wanted to do like a rigid indenter, And so I created a sphere, and then I just extracted a portion of the sphere, the surface, and because it's a rigid material, it doesn't matter if it's a shell element or solid elements. And this is a biphasic layer. So this is a full 3D problem, and I'm going to slide this rigid indenter back and forth. You wanted to do sliding friction with a biphasic material. You also wanted it to be creep, so I'm going to apply a constant force. And then you wanted to lift it up and let the fluid recover. So those are the things you asked about. So I'm just going to describe what I did briefly, and then of course, if you want to go step by step with me, we can do a separate call. So what you need to understand is we have two materials here. One is the cartilage material, one is the indenter. You want to do a creep problem. So when I created the sphere, I initially created the sphere so that it was like it had a point tangency with the cartilage. But if you're going to drop a load on the indenter, anytime you do a creep problem for a contact analysis, you need to allow the surfaces to overlap a little bit initially. Otherwise, at the very first time point, the fine element code doesn't see any contact, and then it fails. You get a rigid body motion. So I used the translate tool, which is here. I took the shortcut command, and originally I think I had it at, this was where it was originally. So that was like perfectly tangent. And then what I did is I moved it down. How much you move it down, it's up to you. I moved it by 0.1 millimeter. And for this particular analysis, that worked. If you overlap too much initially, you might get inverted elements, so you don't want to overlap too much. And just to give you dimensions, this is 20 millimeters long in this direction, 10 millimeters long in the depth, and 2 millimeters thick. So all the units are in millimeters. I applied a load of 5 newtons on the rigid body. So this is a rigid constraint. So I have a prescribed Y force. The value is, this is just a load curve. So it's a scale factor. From time 0 to time 1, it goes to 1. Then during the whole sliding, we're going to slide back and forth. I'll show you in a moment. And then you want it to unload it. So it unloads from time 11 to time 12. Okay. So, but actually, believe it or not, we're not going to use this part. What we're going to do is we're going to do a 2-step analysis. So first, let me finish since I opened this. So this is the sliding in the X direction. So during the first second, I'm going to apply the load, so I'm not going to slide. Then I'm going to slide by however much I specify in the X direction prescribed motion. It's going to be 5 millimeters in one direction, and then I'm going to completely reverse the displacement. And finally, by time 11, I'm going to return back to the initial position. At that point, what I'm going to do is I'm going to run a second step. So I have the loading step where I prescribe a load, but when I unload, I don't want to just decrease the load. I actually want to displace the rigid indenter up, because if I displace it, it doesn't matter when the indenter separates from the surface of the cartilage, there won't be any problem because you constrain the motion. If you simply unload it back to 0, it may, you may still have a little bit of contact. It may have a hard time preserving that contact at a single point, and it might actually fail. So I switch from load control to displacement control. So to do displacement control, that means that at the end of the 11 seconds, I have to do an upward Y motion, and I have to put that in the second step. You see, so the prescribed Y force is in the first step. The prescribed X motion is in the initial step, so it applies for the whole analysis. But the Y force only applies until the end of the first step. Then at the start of the second step, we'll do the unloading. So I need to make sure that my unloading displacement is starting at the correct instant. So if I go back to the upward Y motion, you can see that it's at time 11 that I start moving it up, okay? And so how much am I moving these things? Well, I'm, this is the fixed constraint. This is the prescribed motion, 5 millimeters in each direction that multiplies the load curve whose maximum value is 1. This is the force. it has a load curve that goes from 0 to 1 back to 0. I'm going to apply -5 newtons. And this again is the upward motion. I'm going to move by 1 millimeter up, which is plenty enough to separate the contact. Okay. Let me know if you have questions, along this way. So when I do this and I run the analysis, well, this is a fully 3D problem, so I'm not going to run it here because it actually takes quite a bit of time, but I'm just going to show you the results. So here's the plot file. If I double click on here, oh, I'm sorry, this is the solution file. If I double click on it. So let me just play the animation first. You're going to see it's coming down, moving to the right by 5 millimeters, and then back a total of 10 millimeters back to the center. And then it's going to move up because I'm unloading. Okay. So, and you can see the time increments it took are all like 0.1 seconds. So it really had no difficulty with this. Now let's take a look at the fluid pressure, because that's always the interesting thing that's happening. So what you're going to see is, the indenter, of course, is in the way, but I can hide the indenter temporarily. You can see the fluid pressure is positive. But when we start unloading, what you're going to see is that the fluid pressure may become negative in some places. So, because now there's suction where it's unloaded, the fluid is going in. So how do I know? I can actually plot the fluid flux. So if I go here and I look at the fluid flux vector, and I have to scale it up because the fluid flux tends to be very small. And let me make the material somewhat transparent. And let's rerun the analysis from the start. Now the indenter is hidden, but if I actually temporarily take away the transparency, you can see that inside the contact, there is actually no arrow coming out. If you see tiny arrows, it's because they're like layers of the biphasic material below. And then in the opposite direction, so again, I have to go back to making it transparent. At some point at the, as we unload, the fluid velocity is going to reverse itself. You see some arrows are now pointing down, and then there's only going to be arrows pointing down at the end. I have to zoom in. Well, actually, most of them are pointing down, but somewhere deep. It's a complex response. Okay, so it's entirely doable, but you have to think and plan these things. You have to plan the idea that the unloading has to be a second step because you want to do it under displacement control, because you decided to do a creep, loading. So it's a load control contact. So at the end, when you want to unload it and you want the indenter to separate from the cartilage, if you were doing it under load control, it wouldn't know where to stop. And then it would fail. The analysis would fail. Okay. Do you have questions?
Thank you, Dr. Tishiania. It is really helpful.
Okay, good.
Thank you.
Okay, so we're back to the submitted questions, and we're down to this question by Ru Tao. He is using traditional FEM software like LS-DYNA, and he was wondering about the difference between FEBio and LS-DYNA. So LS-DYNA is a commercial software that was developed by John Hallquist at Livermore Software Technology Corporation. John used to be the lead software developer for Dyna 3D at Lawrence Livermore Labs in the 80s. And he left the lab to start a company, and took with him some of the technology that he had developed while working at Livermore, and created LS-DYNA. And so originally LS-DYNA and Dyna 3D were quite close in their capabilities. But over many years, they've enhanced LS-DYNA substantially to where there are many fields where the software is kind of the de facto standard, especially in the auto industry and to a lesser extent in the aerospace industry. And so LS-DYNA and Dyna 3D started out as explicit time integration codes. And so what that means is that these codes march forward in time, taking very tiny time steps that are determined by the Courant stability criteria, which essentially describes how fast a sound wave can move through across an element. And so these codes are conditionally stable, which means that the time integration scheme is stable as long as you stay below this criterion for all the elements in the mesh. And so typically that results in taking time steps that are on the order of microseconds, sometimes smaller, and for engineering materials. And so generally speaking, codes like LS-DYNA that use explicit time integration are designed for events that occur over very small pieces of time, like fractions of a second. And some of the classic examples are things like automobile impact or ballistics, explosion of weapons, those kinds of things. That's why this technology was originally used at Lawrence Livermore. Some time ago, I would say probably about 15 years ago, LS-DYNA added an implicit solver. So that's very similar to the implicit solver that's used in FEBio. And they use some of the same types of approaches that we do. LS-DYNA also has a pretty decent, quite a large constitutive model library and a pretty decent collection of constitutive models that are specific for biological soft and hard tissues. So, it's certainly an option for doing many of the things that you can do in the FEBio. However, there are many things that FEBio does that LS-DYNA does not. And so some of those things are most apparent in the mixture formulations that are in FEBio that deal with multiphasic materials, transport of neutral and charged solutes, et cetera. And so many of those capabilities are motivated. Their motivation is to address specific biological problems. So although there's overlap between LS-DYNA and FEBio, they're not 100% overlap in either direction. So I would say that if you're interested in doing something like simulating an automobile crash or sheet metal forming, those kinds of things, you might be better off with LS-DYNA. But if you're focused on problems in biomechanics, I think that FEBio is a better tool. There's certainly a good amount of overlap, though. Is Ru available? Did I answer your question, Ru?
Yes, thank you so much.
Okay, great. And if you have any other questions about differences between those codes, just reach out to me.
Sure, thank you.
Okay, so this is the last question that was user submitted before the workshop, and if we have time afterward, we can address some other questions. So this first problem here, I think that we solved this issue, or Steve solved this issue. Is that correct, Steve?
I'm not sure what this problem refers to. I don't
It
think
was
I
a
saw
plot
this.
variable. It was just a plot variable that
It's just a naming of a plot file variable. So I wrote Jonathan back and explained to him that it's Gerard was the one who identified that the plot file variable had changed. Is that correct? Either way,
you guys figured it out on your own, but I confirmed it.
Oh, I remember it now. Yes, it was the plot variable. Yeah, the nodal fluid relative velocity or something like that.
Yeah, I think the variable name had changed, and changing that variable solved this problem. So that takes us to this question, which is, as far as I can tell, probably longer than the 17 minutes that we have left. But
I can do the same thing that I did with Shaniwar, which is just to show an existing problem without taking
Perfect. Okay, that's great. Let's do that then, Gerard.
Okay. So in anticipation of this, Jonathan, I just want you to know that I uploaded the two problems that are in the case study that Jeff pointed out to you. So let me show you the case study. We have a case study in the knowledge base that illustrates pulsatile flow, but the case studies was actually done specifically to also emphasize this new biphasic FSI material, which you may not need. But so anyway, so flow regulation using biphasic FSI domains. I'm going to just describe the second problem because you wanted pulsatile flow. So basically, I'm going to illustrate this problem where the flow enters from one end, leaves from the other end, but there is a muscle contraction in the yellow wall. Okay, that's not exactly what you asked. You asked for a simple problem in your question. You want a velocity inlet, you want a pressure outlet, and you want this to be an FSI domain. So what you asked for is actually easier than what I'm going to describe. So I just want to say, again, one-on-one, we can meet you and I can take you through exactly what you want. So I'm going to just open this up. So I'm downloading it. And well, of course, if I download it, I have to run it. But unfortunately, I don't, it takes like a few minutes to run it. So I'm actually going to go to my directory where I keep these problems. And I'm going to open the plot file here. So basically, let me illustrate to you what this does. There's going to be, I'll show you the fluid velocity relative to the solid. So what happens is the fluid is, being expelled as this muscle contracts for whatever was inside. Now, fluid is entering as the muscle relaxes, and the process reverses itself. Now there's contraction, this end opens, and the fluid is exiting. To better see this, once again, it helps to actually display the nodal fluid flux vector, and if necessary, to scale it up. I don't know by how much. Whoops, that's too much. Let's say by 10. 10. So you can see the fluid exiting. Okay, these arrows are way too big. Or I can say auto scale. This way you don't have to worry about the size, and the fluid is entering. Oh, I know what. I need to make the fluid domain transparent, so it'll be easier to see. Okay, so basically, in this case, I have a valve that opens here initially. So I have these two domains, the one on this end and the one on this end, which have different colors. This one, the blue and the magenta, and they open and close, meaning they either allow the fluid to come in or not. So then when I first contract the yellow muscle, if you want, it turns out that the magenta domain is open and the blue domain is closed. And this is an FSI domain here. The blue and magenta are biphasic FSI, where I can control the permeability as well as the viscosity. And so what I'm doing is I'm shutting down the permeability here. I'm making it very low, and here I'm making it very high. So as this yellow chamber contracts, then what happens is the fluid is naturally being expelled. And that's what you're seeing. Okay. And then at the end of this, contraction, then, so this is at time, 0.5, the contraction ends. Now the permeability is switching. So I can actually display, no, I don't have the permeability here, sorry. But I could have, I should have plotted the permeability. Anyway, now I'm opening this end. So what's going to happen is, other than some like weird transient initially, what's going to happen is, as the yellow wall is naturally going to expand under its own elasticity. So the muscle force has been, is being decreased. So the wall is expanding naturally under its own elasticity. Fluid is entering from this end, but it cannot exit here because this has been shut closed. So that's what's happening, and then it repeats itself one more time. So what I want to emphasize is that the analysis time for this model was not that bad. I don't have it here, but it was like a 7-minute analysis time. So you don't have to do, just because it's FSI, biphasic FSI, doesn't mean that it has to take hours and hours to run, right? So if I turn this off, and if I go back to the vector plot and I hide it and I turn on the mesh, you can see that the mesh is relatively coarse, but you need to have this boundary layer here because the fluid velocity relative to the solid wall is going to be 0. Okay, do you have any questions, Jonathan?
Maybe, yeah, thanks, Jarv. That was awesome. Perhaps you can just comment on the boundary conditions for the pore fluid on the or even at the interface between the biphasic end caps and then the primary fluid. What are the boundary conditions there?
So what we have is the boundary conditions are like fixed fluid dilatation when you want 0 fluid pressure. So you can have that just go down. And there's no prescribed pressure in this particular problem because this is really, the flow is driven by the contraction of the muscle. But let's say that you wanted to prescribe So this is your boundary condition. Let's imagine that the blue region is the same properties as the other regions. You can select this face and you can go to add surface load, and you can prescribe a fluid pressure here, whatever fluid pressure you want, right? So let's say you prescribe the fluid pressure and then you associate a load curve with it, so you can make it pulsatile. Or if you want the, right, and so here is, the inlet, right? So if the inlet is a prescribed fluid pressure, you should also kind of keep in mind that the fluid velocity in theory can come from any direction. So it's probably not a bad idea to also fix the fluid velocity in the tangential direction, in this case in the y and x direction. I would constrain that, right? So that the fluid only moves in the z direction on that interface. Because, in reality, there's some kind of, domain upstream that you're not modeling explicitly. So it's okay to assume that the fluid is coming in only along the z direction. There are other things that you can apply. You can also, we have a load option called a fluid flow resistance. Flow resistance means that you actually have a pressure that's proportional to the flow rate that's coming out. So you can actually prescribe a resistance value here. So the resistance value is pretty much going to be it's like a, voltage is resistance times the current, right? So the current will be the flow rate and the voltage would be the pressure. So how much pressure do you want to build up for a given flow rate? You put a resistance in the correct set of units. So that pressure might still not be the pressure that's realistic. What if this is actually a section of an artery, and you know that you want the arterial pressure? Then you can put a pressure offset on here. The pressure offset will say, I'm going to add, 760 millimeters of mercury, or whatever, 100 millimeters of mercury, not 760. Let's say 100 millimeters of mercury, on this face downstream, on top of whatever flow resistance I want to prescribe. So those are the types of, options that you have. If you want more complicated, like RCR with the capacitance downstream, actually we have implemented it in the code, but we haven't documented it. But if let's say that's something that you need, just reach out to me. Share a model with you that has that feature. Does that answer your question?
Yeah. Thanks, Jar. I think I'll take you up and meet with you individually as well to go through the even simpler version.
Okay, no problem.
Directly. Thank you so much.
You're welcome.
Okay, I think that takes us through all of the pre-submitted questions. We still have a few minutes left if anybody would like to ask a question that wouldn't take too long to answer. Going once, twice.
We got a question.
All right, just under the wire there. Let's see here. I believe, Jeff, you mentioned that sometimes it's just not feasible to use uncoupled materials, since FEBio does not output that variable for coupled materials. How can we characterize the deviatoric strain energy, for example, in those cases, or can we not decouple the strain energy in those cases? Well, you can always separate the stress into different components, but in general, for a coupled material, by definition, there's going to be the volumetric, the deviatoric, and then the coupled part. So I don't think that there's any way currently to do this, what you're asking about for the coupled materials. I mean, you can't get the strain energy separated, but you could look at the different components of the stress itself. There's no way to separate the strain energy contributions in that way. So you can always decompose the stress tensor itself into the volumetric and deviatoric parts, but the strain energy is not uncoupled in general. So I hope that answers your question, Amy.
But manually, you can always extract the strain tensor, get its invariance, and then plug it into any equation where you only have the term that you want to look at, right? So remember, you're just calculating a scalar. So for every element in the domain, you can output the strains and then get the invariance from that. So remember that there's always that capability. You just have to export it, let's say, to an Excel spreadsheet and do the calculation there.
Yeah, I guess in that vein, you know, if you're writing your own plugin material, you can also extend FEBio to output other fields that you might be interested in. So if there are specific terms that you're calculating in the constitutive model that you want to look at, it's possible to output those terms to a plot file database.
And I do want to add that you can specify, you can output both the strain energy, the total strain energy, and the deviatoric strain energy of an elastic uncoupled material in the plot file. So there are special plot variables that allow you to look at the total strain energy as well as the deviatoric strain energy.
But not for coupled material. I think that was the question. And you have to understand that separating the deviatoric, like the distortional versus the dilatational contribution, is only straightforward for isotropic materials. It's not a straightforward thing for anisotropic materials.
Can I maybe add on, or like ask a follow-up question on that? Is that because we don't currently have the equations to do so, or like is it because of the math, or is it a physical thing that is preventing us to do that, from doing that?
It's a theoretical issue, not,
yeah,
you know, so if the theory is there, we can implement it. If it were straightforward, we would do it.
Okay. Thank you very much for all your responses. Thanks.
Welcome. All right, any other questions from the group before we sign off today?
And I think I asked this in the chat before too. Can we optimize to multiple forces in multiple directions at once? I think I asked that before. It wasn't possible before, but I guess I'm just trying to see if there is an update on that.
Yeah, there's only, you can only specify one reaction force curve or one curve, you know, regardless of what it specifies. So that has not changed now.
Okay. Yeah. Thank you.
Mm-hmm. If you can send me some more information on what you want to do, I can look into adding that capability, because I think it's not the first time that something similar comes up. So send me an email with a little bit more details, and then I'm happy to look into this a little more.
Okay, great. I will get in touch with you, Steve. Thank you very much.
Great. You're welcome.
Bye.
All right, I'm amazed that the timing worked out as well as it did. When I first looked through all these questions, I thought that there's no way we're going to get through all of these, but fortunately, Professor Ateshian put some homework in before we got started here, so we were able to move through some of the tougher ones at warp speed. So anyway, hopefully this workshop was helpful to you. You know, we're certainly interested in doing more of these kinds of workshops. You know, our standard contribution to SB3C has been kind of a 1.5 hour tutorial or workshop or demo, and it's pretty hard in that format to really you know, address individual user concerns. And for about 5 years in a row, we got around that by hosting a 10-day course in Park City, Utah, where we talked about FEBio extensively, and the users found that very helpful. But NIH in its wisdom decided that they didn't want to fund those types of workshops anymore. So now we're just kind of doing them as we can. And so hopefully, if this was successful and you appreciate it, we'll try to continue to do these things in the future when we can all get together in person. And you know, frankly, I think that's going to work a lot better, because then we can do, like, you know, a whole day or something like that, and then have a number of TAs available to help run around and answer individual questions. So with that, I just want to thank you for your attendance, and I want to thank Jonathan for helping us organize this and pushing us to do it. Even in the wake of the global pandemic, we're able to help you run FEBio.
Thanks, Jeff. I appreciate it. Again, a big thanks to Steve and Jeff and Gerard for taking the extra time that it really required to get ready for this in the way that we wanted to do it. And to echo what Jeff said, plan for next year, right? The in-person nature of this, and the ability to see people face to face and help people face to face longer than 3 to 4 hours, which is our Zoom limit these days, is really the plan. So I'll leave you with just a reminder that you'll be getting a survey request from me in the near future, and then we will also try to get this video to you as soon as we possibly can, in the best way that we can. So stay tuned for that. But again, thanks for coming, and thanks you guys at FEBio. Again, thanks. See you in GatherTown.
Okay, you guys take care.
Thank you.